Let's start. In this introduction, we have gone through the concepts of trees and binary tree. We'll focus on the traversal methods of the binary tree. Okay, so we know that understand the difference between the different tree traversals methods. Be able to solve pre-order, in-order, and post-order traversal recursively. Be able to solve pre-order, in-order, and post-order traversal iteratively, and be able to do level order traversal using BFS. Okay. Yeah. So traversing a tree. Yeah. So these are all valid problems. Like any problems. In the interview, I highly doubt in kind of like very good companies that they will be asking you to come up with or solve the or code up the in order or post order pre-order traversal directly. But I'm pretty sure if they ask any tree related problems, you will have to understand this basics, how to traverse a binary tree, and how does that order impact that particular problem. So it is definitely very useful to understand the traversals. Let's go with this one. Introduction of the traversal: pre-order traversal, in-order traversal, post-order traversal, and then in all these three traversal, how can we do it using the recursive approach, and how can we do it using the iterative approach? Iterative approach meant to say, rather than using the systems recursion or the systems call stack, we should be able to code it using our own data structures. Okay, so let's see. Pre-order traversal. Pre-order traversal is to visit the root first, then traverse the left subtree, and finally traverse the right subtree. Here's an example. Okay, in this following animation, the highlighting in the red indicates that we return from the visited node. The order of the visit is indicated on the array right below the binary tree. Okay, you can see this one, that pre-order will be pretty much populated here. So first thing is like we can see here. First thing is okay, this is an empty state. So first step will be the current or the root node will be traversed. Second thing they mentioned is left subtree, not the left node only. The left subtree will be traversed. So once F is traversed, B, which is the root of the next subtree, and then after B, its left subtree should be traversed, right? So its left subtree, so A would be traversed. And then is there any more tree left, or as a left subtree of A? There's nothing. So once the left subtree of the B is traversed, like the current node was traversed and the left subtree, and then the right subtree. Right subtree is this one, which is D. Yeah, D is traversed, and once D is done, D is the for consider this as an isolated tree. For this also, pre-order traversal means first current node, and then its left subtree, which is C, and then its right subtree, which is E. So once this is done, nothing else is left in this tree, nothing else is left in this tree, and here for F subtree, the whole of the left subtree is traversed, and then it comes to the right subtree, which is G. So once G is traversed, so this is just going up above the tree, and then once the G is traversed, it will look for its left subtree. There's nothing existing, so it will go for its right tree, which is I, and then I's left subtree, which is H. So that's it. We are done. So that is the pre-order traversal. In the same way, in order traversal, it starts from the left subtree and then the current node and then the right subtree. So this is pretty similar, but just the order is different. So rather if it was pre-order, F would have been traversed. So now it will go to its left subtree directory, and in its left subtree in this tree, if it was pre-order, B would have been traversed, but it will go to its left subtree. What is its left subtree? What is this this A's left subtree is nothing. So there's no left subtree. So next thing is the current node. Current node is A. So it will start with A. So for B, its left subtree is traversed already. So the current node, which is B. Once the current node is done, it will go to its right subtree. So I hope you understood that one. So you can see this one. it came to A, and then next it should be B as we discussed, and then it goes to its right subtree. In right subtree, would it print BD? No, it will print in order of this tree. In order of tree means first it will go to its left subtree, which is C. C doesn't since C doesn't have any left tree, it will print C, and then the current node, which is G, and then the right subtree, which is E, and then it will reiterate back to its parent node. So the B's left and current and right is done. So F's left is done, but F current node is not printed. So F will be printed, and then its right subtree, which is G. So G is printed. If there was any left child or left tree for G, then it would have traversed left first. But there is no left subtree. That's why G is printed first, and then it will go to its right subtree. In its right subtree, I won't be printed first. It will go to its left subtree, which is H, and then I should be printed. Yeah. So post order traversal, again the same concept. The order is different. So the order is post order traversal is to traverse the left subtree first, then the right subtree, finally visit the root. So in this one, like in the pre-order traversal, again I'll reiterate, we started with the current node and then left subtree and then right subtree. In the in order traversal, we started with the left subtree and then the current node and then the right subtree. In the post order traversal, we'll go with the left subtree first and then the right subtree, and then we will come to the current node. So if we see left subtree which is B, and for travel and not B, the tree consists starting with B as root, and then its left subtree which is A. So A will be printed, and then its B won't be printed, it will go to its right subtree, but D won't be printed, it will go to its left subtree which is C. C should be printed now, and then its right subtree which is E, and then it comes to D, and then it comes to B, and then it comes to not the current node in this whole of tree. It will go to its right tree, which is G, but G won't be printed. G's left subtree, there's nothing in the G's left, and it will try to print G's right subtree. And in this right subtree, first thing is I's left subtree, which is H. H will be printed, and then it will be the right subtree. There's nothing in the right subtree, so the current node, which is I, and then it will be G and then F. So the same logic here. It is worth noting that when you delete nodes in a tree, deletion process will be in the post order. That is to say, when you delete a node, you will delete its left child and its right child before you delete the node itself. Also, post order is widely used in mathematical expression. It is easier to write a program to parse a post order expression. Here's an example. Okay, plus star 5 and then minus 7 2. Okay, you can easily figure out the original expression using the in order traversal. However, it is not easy for you to for your program to handle this expression, since you have to check the priorities of operations. If you handle this tree in post order, you can easily handle the expression using a stack. Each time when you meet an operator, you can just pop 2 elements from the stack, calculate the result, and push the result back into the stack. Okay, I did not understand it completely. Let's see. In order traversal we were done. Typically binary search tree, we can, in binary search tree, this one, we can retrieve all the data in the sorted order in the in order traversal. We will mention that again in the binary search tree part. So why they have specifically mentioned it as binary search tree means we are discussing the general binary tree, as I mentioned before. In binary tree there are no rules. In binary search tree there is rules that all the nodes in its left subtree is less than or equal to the parent node, and all the nodes in the right subtree are less than or greater than or equal to the parent node or the current node. So that the rule must be followed. That's what makes it binary search tree. That, like, binary search tree means, like, basically with every, like, whenever we need to search something, with every step we can reduce the like search space to half of the original. Like if we are searching through 100 elements, if it was an array, like we have to go through each of the 100 elements in an array. But in binary search tree, what we can do is, okay, first step is we will go to the middle element and or the node, and then we are sure that all the nodes or all the left side of the tree is less than that node and right side of the tree is greater than that node. So we can just compare the value with the current element in the node, and then we will, based on that, we would know whether it's in the left part of the tree or right part of the tree. And then we can, like, that's how we reduce the search space into half. And then we will go to the left part, we will search with that node, with the parent node in that left subtree, and then we will reduce the search space to half again. So that's why the searching or finding an element takes an order of O of log n in binary search tree. That rule is not applicable for a general binary tree. In general binary tree, it just means that there is a every node in the tree will have or every parent will have maximum of 2 children, either left or right children or both of those. So here they are trying to state the application. So in order traversal, make sure that the traversal renders the values in a sorted order if we were using binary search tree, not the binary tree. And post order traversal, let's see. In the post order traversal, let's see this one. Since I did not understand this operations part. Post order traversal is to traverse the left subtree first, then traverse the right subtree, finally visit the root. Here's an animation. Okay, we understood what is post order traversal. It is worth noting that when you delete nodes in a tree, deletion process will be in post order. Deletion process will be in post order because, I don't know, that is to say, when you delete a node, you will delete its left child and its right child before you delete the node itself. Okay. Also, post order is widely used in mathematical expressions. It is easier to write program to parse a post order expression. Here's an example. Okay, here let's see. So left subtree, right subtree should be values, and then like whatever, like left subtree and right subtree are kind of operands, and uh, the node itself is like an operation. So let's see if we try to get this one. So we will go to its left, we'll go to its left, that is 4, and its right, which is like, again, its left, 7, 2, 7 minus 2 is 5, 4 star 5 is 20, 20 plus 5 should be 25. That's how the expression should be. But let's see how it is traversed. You can easily figure out the original expression using the in order traversal. Okay. Using the in order traversal. That is 4 star 7 minus 2 plus 5 in order. So in order means left first. So we'll go to its left, we'll go to its left, which is 4. And then current node, which is star. And then left first again. 7, current node minus 2. 4 star of 7 minus 2. And then plus, and then 5. We can easily, okay. It is not easy for a program to handle this expression since you have to check the priorities of operations. So because like you can see this one, 4 star of, like here 7 minus 2 is 5, 4 star 5 it is supposed to be. But if we write it in the in order traversal, how it will become is 4 star 7 minus 2 plus 5, 4 star 7, because star takes the priority, 4 star 7 it would be like 28. That is different from 4 star of 7 minus 2, which is 5. So so in order to keep that priorities, we don't use the post order traversal here. That's what they meant. It is not easy for a program to handle this expression since you have to check the priorities of the operations first. If you handle this in a post order, if you handle this tree in post order, you can easily handle the expression using a stack. Each time when you meet an operator, you can just pop 2 elements from the stack. Okay. Calculate the result and push the result back into the stack. So I think we had solved this using stack before, but we can see when the problem comes. Recursive or iterative. Try to practice the 3 different traversal methods in our after article exercise. You might want to implement the methods recursively and iteratively both. implement both recursion and iteration solutions and compare the difference between them. So usually interviewer might explicitly ask, if they ask to implement this directly, to ask iteratively, because recursively implementing this will be like a couple of lines of code. I'm not saying it's easy, but it's kind of gets the interview over in like 5 to 7 minutes if someone has seen this one. Okay, given the root of a binary tree, return the pre-order traversal of its node. So here the root is given 1. So we need to determine the pre-end pre-order traversal. Pre-order means left, right, and sorry, current, left, right. Current is 1, left is nothing, and right, which is like right subtree. In the right subtree, we will consider current, which is 2, and then left 3. So it will be 1, 2, 3. Yeah, output is 1, 2, 3. Here, if you see current, which is 1, and then left subtree, which starts with 2, but we will go to this left subtree, which is 2 current, and then left subtree, which is 4, and then right subtree, which is 5, 6, 7. So it will be 1, 2, 4, 5, 6, 7, and then 3. There's no left subtree, 8, 9, and then 3, 8, 9. So the same order is given here. Empty tree means it will return empty. And then if it is root 1, just returns the current subtree. Okay, we need to write the pre-order traversal. Okay, here they are asking like if we implement it recursively, they are asking if we can implement the same thing iteratively. So let's start with recursive approach first. So in the recursive approach, as I said, if root is equal to null, we will return null. Okay, let's have this output somewhere here, like list of pre-order output is equal to okay. I'm just following the same constructor approach to keep it clean as usual. I'm not timing these ones, assuming I won't take a lot of time to explain this, but if it is good for beginners to look into this one, might not be good for myself to take a lot of time. I hope I'm being clear in my explanation. Feel free to post comments if something did not make sense there. So here, let's see. Traversal, recursive, okay. I've just made a framework there. Oh, I see that on the screen is not shared properly. Let me adjust that one. So here, the tree node definition is given. If someone's unsure how the tree node is implemented, it will have a value for the current node, and then the left child, and then the right child. Left child is of a type tree node, and right will be of a type tree node itself. And then they have given a couple of constructors, one with the value and one with the left and right, both of those. So in the value, just the value is initiated. They have assumed the value is of type integer. So in the pre-order traversal, what we thought, the current node and then the left tree and then the right tree. So the current node would be added to this pre-order output. So what I'll do, current node dot add root dot val. So added that, and then we have to traverse the left subtree. So left subtree means root dot, let's name it as node here instead of root, node dot left, and then we have to traverse the right subtree. Let's run this code and see. Okay, so did anybody able to find why this error is? It's a silly mistake. If someone find it here, just post a comment right now because I'm going to fix it. So here I have already defined it in the like as a instance operator of this class, but I've again defined it here, and this one is not instantiated. That's why it's assuming this one is not instantiated. This is a separate variable. So let's remove this one. Either I think it's best to mark it as this dot pre-order output, then there won't be any confusion usually. So and here also we can refer it as this dot, but for consistency, let's keep it like this. So now it is sure that okay, this is the pre-order output I'm instantiating here. So this one is instantiated. Let's run it now. Again, it's the same thing. Cannot read the value because parameter is null. Okay, for a particular example could be like cannot read null because cannot read the value because it's null. It's saying why so, like let me explain here. So it is traversing the current node, it printed the current node, and then it went to its left subtree, and then here also it printed the current node and it went to its left subtree, and then it printed the current node and it went to its left subtree, and then its left subtree is null. So it's trying to, what I'm trying to do here is I'm trying to read the dot val of null. So I had done the null check here, but I removed it later on. That's the problem because parameter 1 is null. It doesn't have a field called val. So that is good. So here let's do a null check here. If node is equal to null, then what should we do? We should do nothing. Return, just return. So now it is finished. 1, 2, 3 is the answer and 1, 2, 3 is the expected answer. Let's submit it and it's accepted. And now here it's given. So that's the first part is done. We have a working solution using recursive approach. Here they are saying recursive solution is trivial. Could you do it iteratively? So yeah, as we saw, it is like 3 lines of code removing that null check. So let's try to do it iteratively. So how can we do some or follow some recursive approach using iteratively? So in order to mimic that, I think we usually can come up with or use stack in order to mimic the same thing. I'm kind of thinking the same thing. I haven't implemented a tree using iterative approach or recursive approach for a long time. So let me give it a try. Let's take this one first. Let's leave the pre-order output, this one output as it is. We can use the same thing. I just copied the method signature here. I can comment out the recursive approach, and then here we can start with this one. So let's see. First thing is I said I'll be using a stack of not integer. Let's see, stack of tree node. Okay, and then once I have a stack, it's usually current node, left subtree, and then right subtree. Current node, left subtree, and right subtree for the pre-order approach. So I'll be adding the wherever we started from, start dot push of root, which is the current node, and then I'll mark it as while stack dot is empty. Hi Mahesh. If you have any question, proactively post it. I can explain outside of whatever I'm addressing as well. Like if you have question in whatever I'm explaining, ask me immediately. I can address that. But any other content, if you want me to create or explain, let me know. Thank you. So while stack is not empty, then we have to keep iterating. So what we will do, so we started with root. So first thing is we need to add the current node to the pre-order output. So current node we will be adding to the pre-order output. We don't have to iterate it any further. So let's see, first thing is we need to pull from that stack, right? So p node, I'll take it as current node is equal to stack dot poll. So once I pull from that stack, I'll add it to the pre-order output, the current one, so which is current.val. And once I poll the current node, what I need to do, I need to address the left subtree, not the left node itself, left subtree I'm calling it as. So let's add the left subtree to the stack back. So stack.add current.left. Thank you, Mahesh. Yeah, I'm glad that you found it. Yeah, I'll proceed with this one. Feel free to stop me and ask me or suggest any content that you have. So stack.add current.left, and then I'll be adding the current.right. So first we need to address the left subtree and then the right subtree. So yeah, in the same order. So here, how it will work. So when it is a stack, it will work like the recursive approach only based on the call stack. So now I have added the left subtree. It will take the left one. And then while processing the left subtree, it will add the left subtree first on top of the stack. In stack, how we know, like, let me explain it with an example here. So here, I'll copy this one and let me post it here so that I can explain how the recursive approach is iterative approach is working using the stack. But before that, let's run this one and get done with the coding. So stack.add of right subtree. Once everything is done, I'll have to return the output. Return pre-order output. Okay, I hope it works. Yeah, every time we are taking a new adding something to the stack, and then we are trying to process the current in the stack and adding it to the output and adding the left and right subtree. Okay, so stack.poll, cannot find the symbol stack.poll. Okay, it should be like, if it is a queue, we call it as poll. If it is a stack, we just pop or push. So pre-order output cannot find symbol. What is wrong with this one? Pre-order output. Okay, so this is also here dot add method. So I haven't added the method. Man, I'm making so many errors. Cannot read the val field is null. So the same thing here, 1 2 3. Okay, so if it's left subtree, here I can do two things. I need, like, I think we did the this null check mistake here, right? In the recursive approach, it's in a similar way, but not the same code though. But we need to address those null scenarios in the iterative approach as well. So let's do this one. If current dot left not equal to null, then only we will add it to the stack. Otherwise, we won't. So let's copy this thing. Okay, and then the same thing. If current dot right not equal to null, then we will add current dot right to the stack. Otherwise, we won't. And then we are printing the output. So I hope, I think I'm done with all the errors. I hope everybody can learn from those errors as well. So we did the null check, which was missed. And then the method in this one, like if it is a standard stack that we are using, push pop. If it's a queue, then we use usually offer and poll. Yeah, so that should be it. So this is finished. Let's submit it and see. Okay, so here the expected output is 1389. Okay, 124567389, and then the output we are giving is this one. So what's the okay, so the output expected is 1 2 4 5 6 7 1 2 4 5 6 7 3 8 9. That we know, that is the expected output. So where are we going wrong here? So that's the thing. So we are adding the current value, and then we are adding the left value if the left is not null, and then we are adding the right value if the right is not null. Let's go back to the tree here. 1 2 4 5 6 7 3 8 9. So I have added, for me it's coming as 1 3 8 9, and then 2 5 6 2 5 7 6 4. How does it look? Basically, it's looking like, from this troubleshoot, it looks like okay, it looks like I have been printing the left and right in the reverse order, right? It is supposed to be 1 2 4 5 6 7 and then 3 8 9, but I am printing 1 3 8 7 8 9 1 3 8 9, and then 2 5 7 6 and then 4. So that means I understood what's the exact problem here. So here I'm adding the left subtree to the stack first, and then the right subtree to the stack. So what happens in the stack, whichever we add first will go to the bottom. So we take last in first out in case of stack operations. So last in first out means, so left went to the bottom. After that we added the right, which sat on its top, and then when we are like popping it, the right one is popped first, and then again I added its left subtree and then its right subtree. Again the right one will be popped first. So it's the reverse order in which we need to add. So if we add this one, then it will be fixed. If we had run this scenario in that using the diagram or some written approach, then we would have figured out the same issue. Let's run this one for this example. So okay, this is the question. Okay, let's run this code. Okay, expected answer. So now it is right. So I think for me, I think the coding is about understanding it. Even if we make issues, if we are able to quickly understand like what was the issue um, and troubleshoot it and fix it, I would select them in the interview. So don't get bogged by it's not about a memory test. It's about how neatly you understand the concept and how neatly you can solve the problem there. So let's submit it. Okay. Okay. The credit for the website is it is LeetCode, Appasani or Sandeep, if you are asking. So let's do a null check here as well. The node itself is null. Okay, it's accepted. So let's move on to the next problem now. Okay, we should not take a lot of time for these ones. Let's binary tree here also. Recursion solution is trivial. We need to do it iteratively. So there are two problems. Let's add a timer and then we should be able to solve both of those in 15 minutes. So let's create the same thing. Okay, private. So instead of in order, output equal to okay. We should not repeat the same mistakes that we did last time because we have to learn from our mistakes there. Okay, we have these things. So new array list and we have everything. We don't do we have to solve it in recursive approach as well? I'm not sure. So we can do it if node or if root is equal to null, then just return okay. We cannot do this one here. For recursive approach, let's create a wrapper method. In order traversal recursive and then return in order output, and then we need to create this method traversal recursive. Okay, and in order traversal, we know that let's name it as node, and then we need to do the null check. If node is equal to null, then we will just return, and then this one will not return anything. We are just appending directly to the in order traversal. Would return void, and then here in order means it should be the left subtree, current node, and then the right subtree. Left subtree, current node, and right subtree. So that means left subtree. How would we resolve the left subtree? We will just call the recursive method with the left subtree, node dot left. And then I said current node and then the right subtree. So to the current node means I need to add the current node into the output. So in order output dot add current node is node dot val. So I'm printing that here, list of integer. And then I have made a null check. Is there anything left in this? I'm using the call stack instead of my own custom stack. So the order would be followed. Let's run this one. Again, compile error. Okay, here I didn't name it properly after copying. Let's do the same thing. Okay. And 132, 132. Let's submit this one. Okay, it's accepted. So now recursive approach is accepted. Let's do the iterative approach for the same thing. So I just copied the method signature. Let's comment out the recursive one. And okay, let's create a stack here also, stack of tree node. And then add this. push the root node to the stack, and then while stack is not empty, okay, while stack is not empty, we will have to process that, process each values. Okay, sorry. So that should be popped from the stack. And then here, first thing is we need to process the left subtree and then print the current node and then print the right subtree. So if we add the left subtree first, what will happen next time when we pop, like we will, like, let's say, let's do the wrong way first and then learn from that and do the right way. So now let's add it to the stack. Stack dot add. In the intuitive case, stack dot push, what we will do, here the null check also we need to do. If current dot left not equal to null, then what we will do, we will have to push the current dot stack left to the stack, and we'll do the same thing. If current dot right is not null, then we will have to add the current dot right. Before that, it is like left subtree and current node and then the right subtree, right? So current node means we will have to print that in order that add, in order output dot add stack dot or current dot val. So this is what we have been doing. Again, this will be in reverse order. So what will happen is we added this left subtree that went to the stack, and then we add the current output, and then we will add the right subtree. So the right will go and sit on top of the left subtree. So again, in the next iteration, when we pop it, the right will be taken out first, because last in first out, stack was last in first out. So instead of doing this one, if we reverse this order, so okay, if we reverse this order, uh, we added the right first, so right will go and sit at the bottom, and then we print the current one, and then we add the right subtree, left subtree. So the left will be processed first, and then it will print the current one, and then the other should be processed. So let's see. Okay. Okay, Mahesh, um, I think the whole purpose of this channel, just to be in brief, whole purpose of this channel was scaling my mentoring approach to more people at once. Like I have been doing it uh, on and off. Like I can spend some time, I can have a recurring time with you, and also you can join these live streams. I'm hoping to continue this for a long time. So any questions that you have, you can post it in those videos also. And also, like, I can schedule a call with you and discuss about like how you can start with your approach and how you can improve. Let's start with the basics. I think these are all problems that I'm addressing are very much basics now. So let's go with this ones. But feel free to tune into this live streams as well and be proactive. I can address your questions here as well. I can help you come prepared for these live streams as well based on which concepts that I'm going to talk about, so that you can solve along with me. Yeah, maybe I can have like focused time rather than speaking continuously. I can solve it quietly and then give you time and then explain it after giving that focus time. That would be more productive for both of us, I guess. So let's see how this one works. First of all, we have the in order. Let's copy this image. Okay, I have a stack and I have a output here. So to the stack, I have added the node with value 1. And then I pop that stack. And then there is a value called current. Current is 1 now. I popped that from the stack and stack is empty. And then I added the right subtree to the stack. So that would be the node with 3. And then I print the current value, which is 1. And then I added the left subtree to the stack, which is 2. And then the current, and then the iteration ended in that while loop. So now I came back to here. So once I added 1, okay, I pop the stack again. The current becomes 2. So this is the top of the stack. So I think it's better if we represent it this way. 2, 2, 3, like this. So I popped the 2 out of the stack. So the now current is 2. So what I'll do, I'll add the current right to the stack, which is 5, and then print the current value, which is 2. And then I'll current right to the stack, not to the current. So I told I'll add it to the stack here. When we add it to the stack, it will become top. And then I'll add the current left to the stack, which is 4. So, and then current was printed, and then it is out of the loop here. And let's say I'll pop the first element from the stack again. So that should be 4 here, the current value then. And then the output will be just its right is null, and then it will print the current, and then it will print its add its left is also null, so nothing. So current value is nothing. After that, iteration is over. So once that is done, the current value will be 5. Current value is 5, and then it will come to its right. It will add its right to the stack. Okay, and then it will print the current value, which is 5, and then it will add its left. Left is 6 here. So, but this is not going well according to me, because output is not in the order here. Output I was supposed to be 4, 2, 6, 5, 7, 1, like this. 4, 2, 6, 5, 7, 1. Yeah, I think I'm correct in that one. Yeah, 4, 2, 6, 5, 7, 1. But what I'm printing is, I'm printing the current one based on this one, like 1, 2, 4, 5. So even though I'm adding it to the stack, it is like here in this code. Let's see. Let's go back and refer here. Even though I'm adding it to the stack, once I print it, I'm printing it here. So before this stack being operated, or before I pop it out of the stack, I'm just adding this one. This operation is happening first before this one. So what should I do? How can we tackle that using a stack? Let's see. Using the call stack, it was easy. Like if I just call this method, this it would the control wouldn't even come to this one. It will just switch to this method call and then go there with the node.left. And then in the same way, it would print the left and then only it will come to the current node. Here in this case, that's not happening. How can I simulate that one? Let's see. Let's go back to the design or the drawing room and see. How can I address this one? In order traversal. Okay, current dot right I'm handling, or even if I do current dot left also, it doesn't matter. I need to figure out a way where I um, delay the execution of this statement to after executing these methods. So how can I do that? So this one is pushed to the stack, and then I come back here. I'm somewhat feeling that I might have to push this one also, the current also into the stack again, back again, and then see if the current dot left is already visited or already taken care of. Then I'll what's the problem details? I'm just now getting here. Okay, Donnie, this is just a in order traversal, the basic tree problem, binary tree in order traversal. Let me get one solution for this tree. Let me get a solution for this thing. Okay. So this routine binary search tree problem. So using recursive approach, it's easy to trivial to solve. So I did that using like merely like 3 statements here, which is not visible yet. Let me fix it. Let's take a break for a quick break and then I'll just be back. I have some issue with the screen alignment here. I'm trying to get that thing right. I made some changes in the morning. Okay, still it's not visible here. Okay, I think this seems much better. Yeah, thanks, Johnny. I hope you are getting your questions answered. Let me see. So this is an in-order traversal I'm trying to resolve for tree. So now I'm stuck with how to solve it in the recursive approach. So the recursive approach was pretty straightforward. I'm trying to resolve it using the iterative approach, and I'm stuck in that one. So in the iterative approach, as we saw in this one, so I'm not able to delay the print or the output statement here. So that is the confusion. How can I add it? Like I'm adding it to the stack. I can kind of change the order in which the left and the right subtree are printed, but not able to do this one. So in order to do that, somehow I need to push it back to the stacks and then not print its left and right subtree. So how can I do that one? So let's see. Let me add it to this one. Stack dot push current as well. So if I do this one, when would I print it? That's the question. When would I print it? So if the current is already visited once, then I'll have to print it. Let me add a visited set of tree node visited is equal to new hash set, and then let me do this one since I pushed it here. Okay, if if visited dot contains the current node, which is current here. If it was already visited before, I'll do nothing but adding it to the output. I don't have to add its left or right or anything. Output dot add current dot val. I hope you guys understood this one. So let's see. I haven't still run it and tried this one out. So now after this one, I need to return this. I don't want to add the current dot right. So first time when we come here with this, okay, now I added one more thing. Let me clear these things. Let me clear these things as well, and let's get the code here so that you guys can easily follow this. So this is the code, right? So this is the code. Let's get this one here, and with the current I don't need much, and I need visited as well as another approach, another output. So let's see. Now the stack would be, first thing is, okay, while stack is empty, okay, while stack is not empty, I'll add the, so before that stack I have pushed the root node. So root node is 1. So there is 1 in the stack. And then while stack is not empty, the current would become, I pop from the stack. When I pop from the stack, it will go out of this one. And I have added this to here, 1. So once I add it here, I'm kind of checking if the visited contains the current node. No, it doesn't. So it will go to the next one. If current dot right is not null, then stack dot push current dot right. So current dot right is 3 here. So I push that one and then push. I'm pushing the current to the stack. So current is 1, and then I'm pushing the, if stack dot left is not null, I'm pushing the left to this one. So left is 2. Okay. So once that is done, okay, I'm just thinking about the impact of this stack dot push without doing null check here. So if I don't do null check, then it would okay, let's see, let's go through this one. Okay, there it will be like 213, nothing in the output, current is 1, and then the current is that this particular loop is over, so the current value will be nothing. And then I'll pop from the stack, which is 2, and that will be the current value. Once I pop it out, that is gone. So once the 2 is popped, okay, this is not visited. I haven't marked it as visited, anything as visited. Let's mark that one. Where would we mark this one? So visited.add current. Let's do this one. So visited is of type tree node. So okay. So here, where's that? Visited.add. Okay. Okay, I have added this as visited. So now visited is 1 is already in visited since I added the previous node, and okay, and then now 2 is the current value. So now 2 visited doesn't contain 2. I have added 2 as visited now, and then current dot write not equal to null. 2's write is 5. I'll add that to the stack, and then I'll add 2 itself it to the stack since I'm pushing the current node. So I'm adding 2 to the stack, and then I have to push the left node of 2, which is 4, to the stack. So I push all those things to the stack. So now this current node, this loop is also over, so the current is reset. So now I am popping from the stack again, which is 4, and then until now I haven't printed anything to this one. So I popped the current value, and the 4 is not visited, doesn't contains 4, and then visited dot add current. So visited dot add current. So I need to add 4 to the visited, and then if current dot write is not null, current dot write is null. Current stack dot push 4. So I push the current node, and then current dot left is not null, current dot left is also null. So this also that doesn't verify. So the current also is gone here. So now here I'm checking the stack again. Tree.node current is equal to stack.pop. Stack will become 4 again, and I'm checking if the visited contains current. Yes, it does contain current. Then I'll order that to the I'll add it to the output, which is 4, and then return. Do nothing. Not return. It should be continue. Basically, we should still be in the loop. We should not just exit. So let me correct it. Let's do continue here. Okay. Okay. So now I already popped the 4 out of the stack. I forgot to eliminate from here. And then this loop is also over once I continue. So the current is reset 4. So the current would be 2 now. I pop from the stack, and 2 is also already in the visited. So I'll print it and continue. So 2 is printed. And then again, this left and right subtree, I don't have to, it will continue and exit from this loop. So 2 is also reset. So now the next one is 5. 5 will become current, and 5 is not in visited. I'll add 5 to the visited based on the statement visited.5. Okay, I've taken a Pomodoro timer. That made me full screen now, forcefully. So let's see. Okay, so the timer is gone. Okay, in the config settings, compact mode full screen break is minimized, and then timer is back on. And then here, okay. Got it. Sorry for the break here. So I took 5 as the current value, and that should be removed from the stack. And then I have to add current 5 as visited, and then 5 has right child, which is 7. I need to add that to the stack, and then I have to add 5 itself to the stack, and then I have to add its left child, which is 6, into the stack. So now that is done, current will be reset again, and then I'll pop from the stack, which is 6, and then 6 will be added as visited. Okay, then I'll have to, okay, once I pop from the stack, 6 is gone from the stack. Okay, and then 6 is left child, right child, there's nothing. 6 has current one, so I'll add 6 to the stack, current child, and then 6 is right, left is null, so nothing. So now again, in the next iteration, 6 is the current one, and I'll pop that from the stack, and then it will check if the 6 is visited. Yes, 6 is visited, so I'll have to print 6. So I'll print 6. I mean, add it to the in order output dot add, and then yeah, continue. So it won't do anything. So current value is reset. Now 5 will be the current, and it is taken out of the stack. 5 is already in visited, so I'll just add it to the output here. So 5 is added to the output, and then the same way 7. 7 would be the current now, and 7's right child is not there, so nothing is added. 7's left child is sorry, current value is 7. Once I pop 7, it went out. So it checks for its right, nothing, and it checks for the current one and add it to the stack here. Pushes to the stack. So I'll have to push 7 to the stack. Okay, and then add it as visited as well. So 7 is visited now. And then yeah, and then current will be reset. So now again, 7 is at the top of the stack. 7 will be current, and then it will check. 7 is already in visited, so I'll just add it to the output, in order output, and then continue. So 7 will be moved out of current, and once I took it out of the stack, it's gone from the stack also. So now the next one is 1. So once I come to 1 here, current will be 1, and 1 is already in the visited, so I'll just print it as output and continue. And 1 is not current now. 3 is current now. 3 is current, so nothing in this. 3 is removed from the stack, and then 3 is left child. 3 is right child, which is 8. 8 is there, so I'll add it to the stack, and I'll add the current value, which is 3, into the stack, and I'll also add 3 to the visited node. And current 3 doesn't have a left child, so there is nothing. So 3 is not current anymore. Now again, I'll take 3 is at the top of the stack. I'll take 3, and 3 is visited. I'll add it to the output and then continue. There's nothing. So this is gone, and the current value is 8 now. I'll pop 8 out of the stack, and then I'll add 8 as the current value. Visited value after adding it as current. So 8 doesn't have a right child. 8 has the current child. So yeah, I'm in current node. I'll just add the current node, and then I'll have to add its left child, which is 9. So 9 is added to the top of the stack. So now I pop out 9 from the stack. So 9 is popped out of the stack. There's no left child. There's no right child. But I'll add 9 back to the stack, and I'll add 9 to the visited. Okay, once that is done, there's no left child also, so current is gone. Again, 9 I'll pop out of the stack. 9 will come and pop out of the stack, and 9 is in visited. I'll have to add it as output here, and then I'll have to continue, so nothing else. And then 8 is the next one. I pop out 8 from the stack. 8 is already in the visited, so I'll add 8 is already in visited, so I'll add that to the output here, and then continue. So, and then the stack is empty, so nothing else. So the output is 426571398. 426571398. 426571398. So that's the output we iterated. So we are sure that this approach might work. And how did I come up with this approach? I I never saw this problem in recent days, but the only thing is, this was not my first approach or first intuition to this solution. We were able to solve the pre-order recursive pretty easily. I thought it will be somewhat similar because in there in the pre-order, the order was current node and then uh, left node and then the right node. I had to switch the left and right node order because in the stack I will be popping it in the reverse way. But I thought it will be somewhat similar. But here I was printing it immediately. There the necessity was printing it immediately because the current node was the first one. Here I should not be printing it immediately. So if I just add it to the stack, first add it to the stack, and even if I printing it here, like if I do this in order output dot add here, even then this will be printed first because I'm just adding it to the stack. I'm not actually calling the method here. In recursion, we actually call the method and go there, and the control goes there. Once we execute that method, we will come back and add it to the output. But here, that's not the case. We will just add it to the stack and we were printing it. That wouldn't work. So I need to delay this print. How, like I was thinking, how would we delay the print? So we can delay the print by adding it back to the stack somehow. And once we add it back to the stack, the same procedure would continue. It will look for its left subtree, right subtree, and keep doing that. So we didn't want to do it. So how can I achieve that? How I can achieve that by, if I'm coming to that particular node for the second time, if it was already visited, then I'll just print it directly and won't go to the steps to add the right stack and left stack add the right element and left element to the stack. So that's how I was able to get this visited. I'm not sure what's the standard approach or if there was any approach. I'm pretty sure a modified version of this one should work. I haven't tried it out. Let's give it a try. If there are some small bugs or minor things, we can fix it. Okay. So it worked for a smaller output. Let's see for a custom case, which is what we ran now. I mean, what we simulated in that drawing output. Today I'm seeing a great turnout in the live stream. A lot of people are appreciating. It makes me feel much better, pumped up for solving these problems. Okay, for this one also it worked. Let's submit it and see. Runtime error. So it says runtime error. One thing is I needed to address this later. If root is equal to null, return in order output as it is, like the empty list it will be, and then cannot read field right because it's okay. Okay, here I'm checking. Okay, then that's the same thing basically. The same case that I had not addressed. I wanted to, trust me, but I lost in explaining that. Okay, it's accepted now. So this approach would work. I hope they have given the solution somewhere, but let's see. If they haven't, it's fine. This would work, and I don't see any performance improvement that we need to make. Let's code up the post-order traversal as well. Let's not waste a lot of time in that and go and get to the next type of problems. Okay, it's binary tree post-order traversal in this one. Given an okay, I think the solution was there, I guess, for the in-order traversal as well. Let's look at the standard solution, which was the recursive approach is simple. Yeah, helper dot this thing result dot add and this one root not equal to null. Okay, I think that's a good approach. I just did if root is equal to null return. If root not equal to null, then execute this. Okay. So here in order traversal, let's see. Open. Okay, they have a stack, they have a visited, and then the current node. Well, current node not equal to null. Okay, if current node not equal to null and stack is not empty, if current node not equal to null, Current is equal to current dot left. Okay, they have done something different, I guess. Stack dot push of current. Current is equal to current dot left. Okay, let's leave this one. Current not equal to null. Current is equal to stack dot pop. Okay, this is a little different. Not very intuitive for me. Like who uses stack? Like for me, whatever I have done, like I tried to mimic the how the call stack works, like in the recursion. I tried to mimic that and make it work the same way. But here, I think this could be a better approach, I guess. Let me see. Let me run this one and submit this approach as well. Mine. So this is like beats 2.909% here if we are looking at the percentage. But I'm not convinced that okay my approach was bad enough, because like we had not seen this problem before and we tried to come up and make it work using the stack and the data structure with our knowledge of the data structure and how those operates, which is pretty good. I would be impressed if someone tackles that in the interview the same way. But here there is a simple approach. While current not equal to null and stack is not empty, so they have used stack as well, they have to but yeah, they have the result. So while current not equal to null, stack dot push current. So current is equal to current dot left. So they keep pushing the current node to the stack until they find something where the current dot left is not null. Current dot left is null. So what they meant to say is like here, okay, they come here, they don't do this one while current dot left is not null. They will come to this one, they'll push this to stack and assume the current as this one. They'll push this to stack, assume the current as this one. This left is null, so they will just print this one, which is 4. And then they'll print the current one, which is 2. Uh, and then they will print the 5, I guess. That's right. Current is equal to stack dot pop. Okay, once they push everything in the left one, they'll print the current by taking it from the stack, and then they will print the current dot right, and then they'll just assign that current is equal to current dot right. So next one, it will be like if this one had some nodes on the left or left subtree, this would have kept doing the same thing, keep adding the current to the left stack and keep going. But since this doesn't have any left charge, it will just print the current node here. So that is nice, not a bad approach. I can code it up. Let me see. It's good to know multiple approaches as well, because we are not learning the solution for this particular problem, but we are uh, trying to learn problem solving. There are two things as I see for these type of interviews, two skills which are very important. One is the problem solving skill, uh, which is like any problem given, we need to identify the data structures we can use, and we need to identify like how best we can solve it and how fast we can. How fast means not in terms of the time we take to solve the problem, but in terms of how fast it will run given any input. So that's the first parameter. And the second thing is whatever the approach or things that we think about, we need to translate that into the format of code. So that's when having a programming language with which we are comfortable is the key. Like that gives us a lot of confidence in translating our thought process into the language that is understandable by machines. So uh, yeah, and the reverse is also true. If you want to learn a programming language, I think it's good to gain confidence by solving these problems. This will give you a good basics about the data structures, which is very basic. I have seen a lot of arguments about the LeetCode doesn't translate to any real world problem solving skill. Uh, I might agree about some things, few things like harder solutions like dynamic programming or maybe a few other things which we might never use in our real time. But the knowledge about data structures is like a day-to-day thing. It's like a basic common sense while we are working on real-time things. Um, yeah, it is pretty useful to get good at some particular language while we are learning language. Yeah, let's try to implement how they have given and see if I can make it work as well. Um, I'll copy the method signature here, the same thing, and post this, comment this one. Okay, so let me remove all this. Okay, I have a stack, and if root is equal to null, okay, I'll do the same check here, and then I have a stack, and I'll push it to the stack. Okay, and I'll have to have a current also in this case, right? In the solution. Okay, this recursive is pretty easy. Yeah, they have a current as root, and they haven't assigned anything to the stack yet, because if we added it to the stack, it would have printed it. I think our approach was very good. Like, I feel pretty good when I solve a problem without having any history. Like, I think I had, when I just graduated, I had a couple of interviews. Like, one was like I wasn't very much ready. Like, I had not done so many lead code problems and things like that, but I had done a lot of practice coding in Java. So whenever they asked me in some problem, in one interview, I clearly remember they asked me to implement a heap. So heap data structure, I did not know honestly like about heap structure a lot. So I took the requirement from them, like about how the heap should work, what all methods I need to implement, uh, and how we should design for that. And I was able to come up with an approach which is workable, like on the spot for that heap. And they really gave me an offer in that interview as well. So yeah, I think these things always works. Like, usually the interviewers, I mean the good interviewers, they don't look for your memory or the knowledge that you have about a particular thing, but they will try to assess you based on your ability to translate a requirement into a solution. They know that you will have access to Google or nowadays ChatGPT while you are working on real time thing. But yeah, using that, how will you be able to solve a problem? That's the main skill. Okay, let's implement this one. If root is equal to null, okay, got it. If we don't need a visited in this approach, we don't need to push it to the stack yet as of now. So let's mark it as this one. Ah, this new is like so much in muscle memory. While current not equal to null and or I guess not a stack dot is empty. The stack is not empty. Either of those, either current should not be null or stack should have something. Then what should we do? Another loop here, like we need to keep going left rather than adding the current one to the stack. While current dot left not equal to null, then what we will do, we will mark current as current dot left. Okay, and we need to keep pushing the current one to the stack so that we can keep climbing back those things. Okay, once that is done, we need to add current is equal to stack dot walk. Okay, here current not current dot left, but basically while current not equal to null, so we need to keep pushing it to the stack. And then okay, that means will not push null value, but we will push until null, and current would become null here since the current not equal to null. Okay, current dot left would be null here. No, not that. Yeah, current is equal to current dot left, which is null. So that means I'll push, like I can't assume the current value here. I'm popping the top value from the stack, which is like 4 in this particular example. So I have assigned for current 4 dot left, which is null. And then this is at the top of the stack now, 4, 2, 1 in the same order. I have added it to the stack. So I have taken the current as 4. And then once I take it, I'll have to add it to the output. Let me add it as the output, which is like current dot val. Once I do that, I need to assign current is equal to current dot. So I need to stack dot pop again and assume that as current. So once this is done, it will come to 2 as the current one. So now 2 is current. It will, current is not null, stack dot push. Okay. 2 is not current, is it? How have we solved it? Oh, current is equal to current dot write there, not stack dot pop. Current is equal to current dot write. Current dot write is what? So current was 4, current dot write is null again. So if current, well, current not equal to null, current is null, this is not satisfied, but stack is not empty here. So this is satisfied, so it will come current not equal to null, current is null, so it won't execute this one. Current is equal to stack dot pop. Stack dot pop will give 2 now. So 2, and then in order output will become 2, 4, 2. Now the in order output current is equal to current dot write. 2's write is 5. So okay, and then again it will come here, current not equal to null, but it will push the current actually 5 to the stack, and current dot left is null, so current will become null, but current is assigned stack dot pop, which is 5 again, and it will add 5 to the output. 4 to 5 is the output now. Current is equal to current dot write. So current dot write is null again, so current is null. Current is null, stack is not empty though. Stack has 1 as the last variable in the stack. So yeah, current is null, so it will come stack dot pop, which is 1. In order output, it will add 1 to the output, which is now the output becomes 4, 2, 5, 1, and then current is equal to current dot write. Current dot write is 3, the node with 3. So now the current is not null, it will come, while current is not null, stack dot push this one. So current, okay, current, it will push the current, which is 3 to the stack, and then current will become current dot left, which is 6, and then again it will push 6 to the stack, and then current is equal to current dot left, which is null. Current is null, and we will take current is equal to stack dot pop, which is 6, and then we will add 6 to the output. So 4, 2, 5, 1, 6 is the output as of now, and current is equal to current dot write, which is null, and then it will come here. Stack is not empty again. Current is null, so it won't do anything here. Current is equal to stack dot pop, which is 3, and in order output 3. So 4, 2, 5, 1, 6, 3 is the output now. Current is equal to current dot write, which is null. Now the current is also not null, and stack is also empty. So both of these condition fails, and it will just return in order output. That should be workable. Yeah, it worked. Okay, awesome. Let's move on to the next one now, without further wasting time. Post order traversal now. So now we have a confidence that we can get things working, like any solution. We can make anything work, but let's try to get the best approach there. In the post order traversal, again, recursion solution is revealed. Recursion solution, we know that it is like 2 lines. Let's code it up and let's get it out of the way. So post order traversal, recursive, then root, And then let's do the same thing here. For the in-order traversal, we had created these things. Let's copy it from there and paste it here. And then this is post order output. Okay, and then return post order output here. And then once this is done, we need to call this recursive. So let's copy the signature. Okay, once this is done, the signature is post order traversal recursive. Let's correct that one, and then let's do a null check. If node is equal to null, then we need to just return. If not, then we will execute. Post means left, right, and current. So left, we'll add the left one. So which is like node dot left, and then right, and then the current means, okay, current means I'll be adding the current to the output here. Dot add. Okay, so let's execute this one. Okay, here this should be void. Yeah, okay, this one's accepted. Let's do the same thing using iterative approach. Let's copy the signature and comment out the recursive one. Okay, so the signature is copied now, and I'll be returning the post order output, the same thing. Let's try to get this one. So now the approach is, first thing is we will have to print the left node or traverse the left subtree, and then the right subtree, and then the current node. So in order to do that, what should we do? While let's take a stack, we would need a stack, pretty sure. Let's think of the approach. So we need to print the left tree first. So how we did it last time, let's see if the current node also, tree node current is equal to root as of now, while current not equal to null. What we can do, in the inner loop also, I have it this way, so that I can just get hold of the leftmost node. I'm doing the same thing because the left order is the same as in order traversal. In the post order as well, we need to print the left one first. Current not equal to null, I will be assigning current is equal, I'll be pushing the current one to the stack dot push current, and then I need to add, I need to make current is equal to current dot left. So that would get me hold of the current value. So what I'll do, current is equal to current dot pop. So once I do that, in order, post order output, which is here, post order output dot add current, and then current is equal to current dot write. That's what we used to do, right? So this would make it as in order traversal, because I kept pushing the current one to the stack, and then keep going to the right ones and try to execute the right, keep going the left side, and then try to execute the left side as soon as possible. Once I execute the left side and added it as the value, I'm doing current is equal to current dot right now if there is any right node exists. So I need to now, so this one would be in order again. So once I have this one, r stack dot is empty, this will be in order totally. Once the stack is not empty, even if the current right node is null for 4 here, let's see, here's the example. So we came till 1 2 4 here, and then right node is null, and then we go back to the stack, it will take 2. So once we take 2, it doesn't have anything in the right. So once this is done, I think I need to again print the right side rather than printing the left node. Dot add current. No, this one wouldn't work here. What if I add the post order output? Um, the current is the leftmost one, we need that one. And then current is equal to current dot right. So before getting the current dot right, I need the current dot left somehow. So can we do that? Let's see. So let me try to come up with an approach here. Let's take a break. In the meantime, I'll try to think about this one. Let's take a quick break. I'm back. Let's see. Okay, what were we doing? Let's look into this one. Okay, we solved the binary tree post order traversal using recursive approach like this one, which is simple and straightforward, and using the iterative approach. In the iterative approach, what we did was we just uh, followed we just did it as like the post order, like the pre-order traversal, and then we reversed the output. So basically what we did is, let's copy this code and let's run it in the whiteboard and see how it went. So this is the code that we have. Okay. And then let's take an example tree as well. Okay, let's take this one, post order traversal. Okay, this is the same thing, I guess. Let's take this one as an example. Okay, and now, okay. Okay, let's run this one. So we have taken a stack. So let's initialize the stack. And then for stack, let's leave ample space here. And then we have a current value. And then we initialize both current value and stack. And then we have a post order output, which is post order output. Okay, okay, I don't want to struggle later, so I just extended it. So these three are the variables that we are looking into. We have the stack. Okay, so now we may initialize the current as root which is 1. Okay, and then if current not equal to null, and stack is not empty, our stack is not empty. So here one of the conditions should be satisfied. Now the current is not null because we initialize the current as root which is 1. Okay, now if this is satisfied, we come inside. If current is not equal to null, so what we will do, post order output dot add current. So to the post order output we added current, and then what next, stack dot push current. So we pushed 1 to stack, and then current is equal to current dot write. Current is equal to current dot write means current will become 3. Okay, so that's it. And then we came here, current is not null now again. So current is not null, so post order output add current, so which is 3. And then stack dot push current, sorry, post order output, which is this one, 3, and stack dot push current. So we need to push means it will come on top of this 3. Okay, and then current is equal to current dot write. Current dot write is 8. Okay, got it. So now again, next string, current is not null. So current not null. If current is not is equal to null, let's add it to the output. We added 8 to the output, and then stack dot push current. We have to add 8 to the stack here, and current is equal to current dot write. Current dot write is null, so current will become null. So now it will come to this while loop again. Current is not equal to null. Okay, this condition doesn't satisfy, but there is a or condition. Our stack is not empty. Stack is not empty obviously here. So we will get inside. If current is not equal to null, current is null. So this code block won't be executed. It will come to the else condition. Current is equal to stack dot pop. We pop first value from the stack, which is 8. So now current is equal to the node with 8. And then current is equal to current dot left. We have already printed it, as you know. So once this is traversed, we will be printing current is equal to current dot left. So current dot left is 8 dot left, which is 9. So current will become 9. So here, yeah. So now current, again, current not equal to null. Here also current not equal to null. Post dot output, we will print 9. And then stack dot push current, which is 9. We will push 9 here. And then current is equal to current dot write. Current dot write is null. current is equal to null. So now again we will come here, current is not equal to null. This doesn't satisfy because current is null, but this satisfies, so it will come inside. Current is equal to null, so it won't execute this one. It will come here, current is equal to stack.pop, which is 9, and then current is equal to current.left. Current.left is also null, so it will be null again. So now we pop the stack, so 9 is gone from this one. So okay, now this one, now again again we will come, current not equal to null, it doesn't satisfy, but this satisfies. This line won't be executed. Current is equal to stack.pop, which will make it 3, and then which will remove it from the stack, and then current is equal to current.left, and current becomes current.left. Current.left is null again, so this will be null, so this will be null. And then again we will come back, it's null, we will come to here, but stack is not empty. We will pop the stack, so 1 will be the current, and then current is equal to current.left, so current.left is 2, so we will come to the left subtree now. So now here, no, the current is not null, but the stack is empty, but the current is not null, so we will be able to get inside. Current not equal to null means post order output dot current dot val. So we will print this 2, and then stack dot push current, we'll push current to the stack, and then current is equal to current dot write, which is 5. So current will become 5, and yeah, same thing, print 5 based on this one, post order output dot add, and then stack dot push current, which is 5. I need to add 5 onto the top, and then current is equal to current dot write. 5 dot write is 7, so I'll make 5 as 7. So current not equal to null again, so 7 I'll print, which is current, and then stack dot push of current, so I'll add 7 to the stack, and then current is equal to current dot write. Current is equal to current dot write, which is null. Stack is null now. So now we come back again. Current is not equal to null. That doesn't satisfy. Current is null, so it will come here. Current is equal to stack dot pop, which is 7, and current is equal to current dot left, which will make it null again. So okay, I have already popped 7. Okay, so now again we will go back, and stack is not empty, so we'll be able to get in, but current is null. So current is equal to current stack dot pop, which is 5. I popped 5. Okay, and then current is equal to current dot left, which is 6. So 6, current will become 6. Current is not null now, so we will come and print 6 here. I add 6 to the output, and then stack dot push 6. So I pushed 6 to the stack, and then current is equal to current dot write, which is null. So same routine, it will keep going the same way. So now again we have null as current, so it will come to this one, and then it will pop 6, and current is equal to current dot left, which is null again. Left of null, 6 is null. Okay, and again we will go back. Current again is null, and then we have to pop the current, which is 2. So that will be the current now. Stack dot pop, and then current is equal to current dot left, which is 4. So current will become 4, and then again we will come back here. Current is not null, we will have to add that to the output, and then stack dot push current, which is 4, and then current is equal to current dot write, which is null. And we will do some extra things now. So where current is null, so we will come here, current is equal to stack dot pop, we will pop 4 here, and current will become current dot left, which is null again. Okay, so now current is null and stack is empty. Both of these conditions doesn't satisfy. We will come out of this while loop. So collections dot reverse of post dot output. So we will be reversing these things. So the post traversal output will become, okay, 4, 6, 7, 5, 2, 9, 8, 3, 1. So this will be. So how we usually print the post order traversal? We thought, left child, right child, and then the current node. So here we come, our left tree, right tree, and then the current node. So for one, left tree is this one. For two, again, if we take this tree as individual, so we will print 4. Okay, we'll print this tree. For this tree, left child is null, right child is null. So current one would be printed as 4. And then it will go back to its node. So left subtree is already taken care of. It's right subtree. For this one, again, left subtree. Left subtree we will print 6, right subtree will print 7, and then the current, which is 5. And then for this one, left and right are taken care, we'll print the current one, which is 2. And then for this one, left subtree is entirely taken care of. We will go to right subtree now. So here, left subtree is null, nothing to handle that. It will go to right subtree. So in the right subtree, it will go to left subtree again, which is 9. We print 9, and then right subtree, nothing there, and then 8 here as the current node. And then we will go back to this one. Left and right are handled, so current 1, 3. Here now left subtree, right subtree, both are handled. 1 should be printed, which is the output. So this is the output. Let's think of it, how to remember this approach. Even I'm thinking of that one. Now we know the approach, it's working, and we kind of iterated through the input and the example in the way we have to. But how can we come up with this approach? This is not a memory test, as I mentioned. Like, we should not optimize these solutions for memory because we are not sure. Like, I'm pretty sure we cannot get the same problems that we practice. So what we should get out of solving this practice or out of solving this is the ability to solve any problem given. So now let's see, we know the pre-order, how the order should be 1, 2, like pre-order is current, left tree, right tree. In order is left tree, current, right tree. And then post order is left tree, right tree, and current. So we know that left tree, right tree, and current. So now if we have to simulate it using a stack, that means what we are doing here, we have to and also they are reversing, like left tree, right tree, current. That's the thing, right? So what is easy? Like holding back printing a value, left tree, this one, not just the left value. We don't have to print 3, but we have to take care of the left tree. That's what it means. We don't have to print 3 in the beginning. Like you can see 2 is not printed in the beginning, but the left tree. For the left tree, again, if we go, it's left side, left tree, which is starting with this one, that's what we have printed. And for the right tree means not 5. Right tree means this entire tree. So now again, if we go and handle this individual tree, it is like this tree is left subtree, so which is 6 printed, and then it's right, which is 7, and then current we have printed, which is 5. So in that, when that's the case, like my intuition says, we cannot hold back printing the current value. So now it's like if we just added left, like we need to delay printing 1, but there's no way we can delay this one. So the current one, we will just print it as it is here in these cases. And then we will go to right tree, and then we will go to left tree, because the order is left, right, and then current. But what we are doing is current, right, and left, and then at the end we are reversing the output that we get with that one. So instead of left, right, current, we are going current, right, and left. So yeah, how do we achieve that current, right, and left? So now we come here, we have the root, we have initialized the current value with a root value, and then if current is not null, we are adding that to the output. If the current is not null, we are adding that to the output, straightforward. And then we are pushing the current to the stack. Why we are pushing the current to the stack? Because if we don't push the current to the stack, when we go to handle the right node, we don't have any parent pointer here. So it should be intuitive that, or it should be reasonable that we need to have the reference of the current somehow in order to get to the left subtree. So okay, we printed the current node, and then we are navigating to traverse the right subtree now. So current stack.pushed current, I pushed the current to hold it back for later, and then current became current.write. Okay, current became current dot write. Again, we will do the same thing. We'll print the current and then we will add this one to the stack, current to the stack, and then current is equal to current dot write. Again, we will do the same thing, print the current and then current is equal to current dot write, and we will add it to the stack, push it to the stack. So we have 8, 3, 1 on the stack. So now we have nothing in this one and 1, 3, 8 in the output. So now when the current here becomes null, what we will do is we will pop from the stack. We pop from the stack, and then it is saying current is equal to stack dot pop. Current is when there are no write trees left, then don't print the current one. Just take the current is equal to stack dot pop, which we know that it was the current value once the right side is processed. So now the current is 8 once we pop from the stack, and then we are trying to assign current is equal to current dot left. We have never handled the left side of the tree, so we are assigning current is equal to current dot left, and left also we will keep processing in the same order until we don't find any other element. So once we printed 9 here, we had nothing. So what we did, we just again current will become current dot right, current will become current dot left, which are both are null. So once that is taken care of, like we will have to bubble up current is equal to stack dot pop, and current is equal to current dot left. Okay, that is done. Current is equal to okay, because when we did stack dot pop, it came 3 after 8. It came like the next value was 3. Yeah, already we had popped 8. So next value we popped was 3. And 3's left is also null. So nothing. And stack just has 1. And again current is equal to current dot stack dot pop, which is 1. And current is equal to current dot left, which is 2. And then we will come to handle this tree. This tree also would be handled in the same way. Here we have printed in this subtree like in the order 1, 3, 8, 9. But in the pre-order, how it was supposed to be? It was supposed to be like if we were handling this as the right subtree, sorry, in the other way, we would have gone in the reverse order. Left side, if there is any left child, and then the right child, which is like right subtree, which means a right subtree of this one is 8 comma 8 comma 9. So in this right subtree, the left child, which is 9, 9, 8, and then 3, and then 1. It would have gone that way when it is like left, right, and current. But we did the reverse one. It came from 1, 3, 8, 9. And then here also it's all the reverse case in this left subtree also. So once we reverse the entire output, it will give the post order output. So that's the approach here. Okay, did anybody new join now? Let me know if I have to repeat it. We have been solving the tree tree related problems and the tree traversal mainly. So let me close these things now. Okay. So post order traversal is done. Okay, I refreshed it. The same solution came here. Okay. So now let's move on to the next one. Okay, here they have given the solution for each of those binary trees. Sorry, a pre-order traversal. This is the pre-order traversal recursive approach, and yeah, recursive approach, and in-order traversal recursive approach, which is traversing the left subtree, adding the visit the root, and then traverse the right subtree. Post-order traversal the same way. Simple. In recursive, it's kind of very simple. And then here, taking pre-order traversal as an example, there are several iterative solutions for tree traversal. One of the solution is to use stack to simulate the recursion process. Taking pre-order traversal as an example, in each iteration we pop one node from the stack and visit this node. Okay. So we did the same thing, kind of when tree is not empty, we added the current, and then if right is not null, pre-order traversal was easy. So because we don't have to hold on to anything, because we print the current value first, and then we take care of the left subtree, and then we take care of the right subtree. But in case we are adding it to the stack, we will add the right subtree first, or the right into the stack first, and then we will add it to the left, add the left element, because first we add the right element, so that will go and sit in the bottom, and then on top of that we will add the left element or the left subtree to be taken care of. So when we pop, we will take the left one first, and then the right one keeps piling in the bottom. Okay, so that should be it. Level order traversal introduction. So level order traversal, I think we have already seen it in the graph problem, but it's the same thing here. We will go level by level. Breadth first search is an algorithm to traverse or search the data structure like tree or a graph. The algorithm starts with the root node, then traverse its neighbors, traverse its second level neighbors, traverse its third level neighbors, and so on. So it's pretty evident from this graph here. So we will handle F, and then it should be B and G, and then it should be A, D, and I. So, and then C, H. So F, B, and G, and then A, D, and I, and then it is C, and H. Yeah. So it is like sorted in the level circle. So it's, they have represented in list of list, first level, second level, third level, and fourth level. Typically, we use queue to help us to do DFS. If you're not familiar with queue data structure, you can learn. Okay, let's solve this one. Usually, let's time box it, level order traversal, list of list integer. So let's try to solve it in less than 15 minutes. Let me solve it first, and then I'll explain it in detail if there is a necessity. But we had solved similar problems while we were doing BS, binary, what's that, breadth first search, BFS. So I think there's no need to go very much deep into the explanation. So let's see, here we have a queue, and then we can initiate the queue with a queue dot of root, and then while queue is not empty, then we keep traversing or keep iterating. Here in this case, queue is not empty, not while queue is empty. Okay, 3 node current queue dot here polling is the method in the queue. In terms of queue, in stack we used pop and push. Here it's offer and poll. Okay, so what should we do? We should just level order traversal. So here current level, let's make it as current level, and then let's have another one for next level. We have another structure for next level. So when we have, why I'm keeping that is, let's check for the current level. I iterate through current level now, but we need to keep the other one for keeping track of the next level letter. We can do it like in a couple of ways. Like we can have a single queue, and we can have some kind of delimiter or something in order to signify or differentiate the current level and the next level. That would save space, but I mean, in the worst case scenario, it wouldn't save space. It saves creating multiple data structures. Like I usually see this one as a cleaner approach. That's why in real time also, if I want to code, rather than saving the instantiating of another data structure by keeping a delimiter or something, I would have gone with this one, with this approach. So I'm doing the same thing here. So tree node is equal to current level dot poll. So now we need to do, what we need to do is we need to iterate through each of its children. In this case, left tree and right tree, or left and right are the only two children. In case of the graph, there could be like neighbors, and we would iterate through each of those neighbors. So here in this case, if current dot left not equal to null, then we will add that to the queue, to the next level, not to the current level, but to the next level. and we will do the same thing for right subtree. We added the right one, and then at the end, what happens when the current level is empty? Now in this case, we just process the current level, which is 3, which was the current level, and then we added 9 and 20 for the next level. So now the current level is empty. This would end this loop altogether if we just leave it as it is. So what we will do is, at the end, we will check if current level dot is empty. Then what we will do is, we will make the next level as the current level, and then next level we will initialize with a new array list. So that's what we will do. So now the current level is replaced by the next level, and also what we can do is we can print the next level, or here the intention is to print this one as an output with level by level. So what we can do is, okay, level order output. Can make it as an array list. And then what we can do is, we can add the initial level here. I'm adding all the next level one. So that should be current level, not the next level. To the level order output. And here, before traversing through each of the next level, we know that the next level is filled when the current level becomes empty. That those are all the attributes in the next level. So what I'll do is, I'll add that level order output dot add new array list of integer with the next level. And I should do the same thing here as well, rather than assigning that current level only into the level order output, because current level keeps varying. Like I'm just holding the reference there. Instead of that, I'll create a new array list with current level that will instantiate the new array list with those attributes. Okay, so new array list of q. This one I'm not very sure about this, but we can check this one if that instantiation is possible or not. And then we will return this value once we come out of this one. So here, whenever the current level is empty, I'm assigning that with the next level. In the last iteration, the next level also will be empty. So I know that there will be a empty array list or an empty list appended to this one at the end. So we might have to just remove that one. So here you can see new queue cannot be instantiated. Okay, usually queue is like instantiated as linked list in case of Java. So queue is the abstract class. So here, new suitable constructor for array list of q.node. Okay, so now what I need to do is, I might have to do add all or something. Okay, let's search for this one. Q2. Okay, I have a new array list here, and then let's dot add all of q. Let's dot add all of q. So I'm adding all the elements to this queue here. Okay, So I was not able to instantiate a new array list, but I can add all the elements of the queue into this one. Okay, so yeah, this is even better. I don't have to instantiate anything. Cannot be converted. Queue of tree node cannot be. Oh, so our queue is made up of type tree node, but our output is made up of level order output. So what we can do is, okay, so what we can do is, let's maintain a list of integer managed to the output, current level output is equal to new array list. Yeah, we need this one. And then we can add it like this, current level output dot add current dot val. So once that is done, what we can do is, when I want to add everything into the final output, new array list of current level output, and then I need to instantiate current level output. Okay, if I'm instantiating it, I don't even have to do this thing, I guess. I'm instantiating that as this one. So new array list of integer. I think that is also taken care of. Okay, here level order output dot add all. Where is that? Okay, this is not needed anymore. This is needed as add. This one should be current level dot offer. Next level is new linked list. Since I have initiated it as a queue, array list cannot be assigned to a queue type. So now it is finished. 3, 9, 20, 15, 7. Let's submit. Okay, for the empty list we haven't taken care of because it will be root, and then we added it as root. And let's see why it won't take care of itself. Current level, I have added null to this one. I've instantiated the level order output here, this one. Current level is not empty. Okay, I have assigned null to the current level, so it won't be marked as empty. It will have one element with the value null. So now current is null, and I'm trying to do current dot left, which is null. I mean null dot left. Null dot left will give null pointer exception. So it's better to define these two upfront output, because it's expected to return an empty list if it is null. So if root is equal to null, and let's return level order output when it was empty only. Okay, now this one is accepted. Let's not spend any more time on this one. I hope the explanation was understandable. How much time did we take? Okay, we started when it was 30 minutes and 16 more minutes left, so we spent 14 minutes with the explanation. That's good, I guess. decent pace. We need to speed it up faster because we had seen similar problem in breadth first search. For this one, we should spend lesser time. So the solution is given. In solution, they have the answer and they have a queue, and then they have added the root to the queue, and then they have a current value here. Well, queue is not empty. Size they have taken, size of the queue, and then list of sub answers, new linked list, sub answers, new linked list, and they are doing a for loop within that queue. For int I is equal to 0, I less than size. Okay, size is equal to q dot size. Okay, and currency for the current value. Okay, they are iterating through the size of the queue. Okay, that's how they know. Whenever we come here into the loop, basically they know the size of the queue. So for example, first time when we come by just appending root to the here, so the size became 1. So we are just doing the iteration for one time. So current is, so they are taking current is equal to q dot poles. Current will become 1. Sub answer dot add current value, current dot value, it is 1. Current dot add value, it became 1. And then they are adding the left if there is a left subtree, then adding the left one, and if there is a right subtree, they are adding the right one. And then to the sub answer means like that for this particular level, whatever the solution which was 1, they are adding it to the answer. And then coming back here, they measure the size of the queue again. So now if the both left and right existed, so that becomes 4. So now that becomes 2. So now they are doing the same for loop for 2 times, and then they if all of those contains left and right subtree, all the 2 nodes, then it will become 4. So in the same way, they'll measure the size and they'll keep appending it to the answer. This is good. I wouldn't say clean, maybe. Again, in real time, I would have gone with that way, even if I have to just create another data structure, because the data we hold is same. We will hold all those nodes, but we will hold it in 2 separate data structures in order to keep it separate. But here we are keeping it in the same data structure, but we know how many elements are in the same level. Based on that information, we are trying to make a decision here and then adding it to the sub answer. But this is also smart. Okay, solve 3 problems recursively. Let me take a quick break for a minute. Okay, let's get back now. So let's get into this one. Bottom down solution, top down solution, bottom up solution, and conclusion. Solve trees problem recursively. A tree can be defined recursively as a node that includes a value and a list of references to its children nodes. Recursion is one of the natural features of a tree. We only focus on the problems for the current node and call the function recursively to solve its children. We can solve a tree problem recursively using the top-down approach or using the bottom-up approach. Top-down approach, let's see what is called top-down approach. Top-down means that in each recursive call, we will visit the node first to come up with some values and pass these values to its children when calling the function recursively. So the top-down solution can be considered as a kind of pre-order traversal. To be specific, the recursive function top-down, okay, return specific value for null node, update the answer if needed, and left answer top-down of root.left and left parameters, and for the right answer, top-down approach root.right of right parameters, return the answer if needed. For instance, consider this problem. Given a binary tree, find its maximum depth. Then what we will do? Here we will define the depth of the root node as 1, although often the depth of the root node is defined as 0. For each node, if you know its depth, we will know the depth of its children. Therefore, if we pass the depth of the node as a parameter when calling the function recursively, all the nodes will know their depth. For leaf nodes, we can use the depth to update the final answer. Here is the pseudocode for the recursive solution. Return if root is null. If root is a leaf node, then answer is equal to maximum of answer, comma, depth. Update the answer if needed. Maximum depth of root dot left and depth plus 1. Maximum depth of root dot right and depth plus 1. Call the function recursively for left child and call the function recursively for the right child. Here's an example to help you understand. So here depth is equal to 1, depth is equal to 2, 3, and update the answer. Okay, depth is equal to 3, nothing, depth is equal to 4, and update the answer. Okay, depth is equal to 2, depth is equal to 3, answer will stay as it is. Answer is equal to 4. Okay, so in the same way, I mean in terms of code, root comma integer depth, we have int answer, the final answer, and this is the current depth of the current node basically. So if root is equal to null, we will just return, and if root is not null, then if root dot left is equal to null and root dot right is equal to null, then answer is equal to mat dot max of answer comma depth. So whatever the depth in the current one, if the root dot left is null and right is null, whatever the depth passed at that one, if that is greater than the current existing depth, then we'll update the answer. Otherwise, we will keep the answer as it is. And then maximum depth, we will call it iteratively. If the root dot left is not null and the right is not null, then we will call is equal to null and is equal to null. If both are null, then only we will try to update it, because we know that if either of them is not null, if either left is not null or right is not null, there will be a leaf, and that will be greater than the current answer anyway. That will be greater than the current depth. Then we can go and update the answer. We don't have to update with every maximum value. So we don't have to check this one every time. We can check this one when we know that this is a leaf node and this doesn't have any child nodes. Maximum depth of root dot left, depth plus 1, root dot right, depth plus 1. Okay. Bottom up solution. Bottom up is another recursive solution. In each recursive call, we will first call the function recursively for all the children nodes and then come up with the answer according to the return values and the value of the current node itself. This process can be regarded as the kind of post-order traversal. Okay, pre-order and post-order. Okay, typically a bottom-up recursive function is bottom up of root will be something like this. Return specific value for the null node, and then left answer is equal to bottom up, and then right answer is equal to bottom up of something, and return the answers. In the top down, it was return specific value for the null node, update the answer if needed, left is equal to this one, and return the answer if needed. Return specific answer for null node, left is equal to this one. Okay, let's try to understand it even further. Return 0 if root is null, left is equal to, we calculate it for left and we calculate it for right, bottom up. And then we know the value, everything came. Okay, in top down, you saw in the depth clearly, we know the depth of the current level when in the root level, and then we have to pass the value further down in order for the leaf nodes to understand its depth. And then when we are in the leaf node, then only we update the answer, whole answer. So top down, the information is passing top down, and then we updated the answer when we are at the leafmost or the bottommost node or bottommost tree node basically. Here is an example to help you understand how it works. What is this problem? Find maximum depth in this. In this one is also find maximum depth. In this case, we are in E, we came to B, and we came to A. Left answer is equal to 0, right answer is equal to 0. So if A's left node is null, A's right node is null, so both of them just returned as 0. If the node is null, then we will return 0. And then at A, we will return it as +1. So depth is equal to +1. So the depth of this one is maximum of the depth of its left child or the right child +1. And then maximum of the depth of its left child we know, which is 1. Maximum depth of its right child, it's not determined yet. Left answer only we know 1. Right answer is we know this is 0, 0, and this will become 1, and this one will become 2. So the right answer becomes 2, 2 here. So maximum of 1 and 2, that is 2 for B also. The depth of B is, okay, sorry, 3. Depth of 2 is maximum of this one plus 1 because it's one higher. So the depth is 3. And then this one maximum, the depth of E is maximum of depth of left child or maximum of depth of right child and maximum of both of 2 plus 1. So this one is 3. We haven't determined for the right child, which looks like 1 and 2 for this one for F. And then this one will become like maximum of 3 and 2 plus 1. Maximum left answer is 3, right answer is 2. Maximum of these two, which is 3 plus 1, which is 4. Depth is equal to 4. So it is like bottom up. We are getting the answers from bottom up while coming back from the recursion. Okay, you can see here root is equal to null, return 0. Left depth, maximum of depth. Okay, right depth is this one. Got it. It's not easy to understand the recursion and find recursive solution for the problem. It needs practice. When you meet a tree problem, can you ask yourself two questions? Can you determine some parameters to help the node know its answer? Can you use these parameters, the value of the node itself, to determine what should be the parameters passed to its children? If the answer are both yes, try to solve using a top-down recursive approach. Or you can think of the problem this way. For a node in a tree, if you know the answer of its children, can you calculate the answer of that node? This is the thought process I usually follow. You can think of the problem this way. For a node in a tree, if you know the answer of its children, can you calculate the answer for that node? If the answer is yes, solving the problem recursively using bottom-up approach might be a good idea. In the following sections, we provide several classic problems for you to help you understand the tree structure and recursion better. Here in this one, can you determine some parameters to help the node know its answer? Can you use these parameters and value of the node itself to determine what should be the parameters that we can pass down to its children? Okay, we should know the answer for the current node, and then with that parameters and help of the value it has, can we pass down the values to its children? If the answer is for both is yes, try to solve this problem using a top-down approach. Maximum depth of the binary tree. Again, we will go back to our basics here. I mean, whatever we saw here, if root is equal to null, return 0, otherwise in left depth is equal to max depth of root dot left and then right depth is equal to maximum of max depth of right dot left, and then return max dot maximum of left depth comma right depth plus 1. Okay, yeah, this works. I think we solved it in like few seconds only. Let's see, can we reset this one? Okay, yeah, we can. Okay, we can turn it on when we need. Let's move on to the next problem. Symmetric tree. Given the root of a binary tree, check whether it's a mirror of itself, that is symmetric around its center. Okay, so now in this case, my thinking is we can compare the nodes as we go along the left subtree traversal and the right subtree traversal. If it is equal, then it is symmetric, otherwise it's not. And also it should not be equal, I guess it should be reverse. So in this one, whatever the left child is, the right child should be the same thing. And then whatever the right child is, the left child should be the equal. So here checking the mirror, in mirror it shows the opposite of left and right, right? So that way, so here this is not a mirror. If this 3 was this side, that would have been a mirror, or this 3 was this side, then that would have been a mirror. Now it's not. So let's check this one, how we can solve it. If root is equal to null, return true, otherwise what we can return, if root dot left not equal to root dot right, or root dot right okay, it's root dot left not equal to root dot right. Okay, I'm not thinking straight here. This isn't right. How can I just keep pursuing? I need to keep traversing simultaneously in both of those. Can I do that? I know that it's a symmetric tree. Yeah, so in order for this one to be a symmetric tree, this one should be a symmetric tree. No, that's not true. This is not a symmetric tree, right? So this is 2, 2, 3, 4. is 2, 4, 3. No, this is symmetric tree actually. 2, 3, 4. Yeah, this should be a symmetric tree. And then for this one is also a symmetric tree. I need to keep checking. For this one should be a symmetric tree. And then I know that, okay, for this one. And overall also I need to compare this one. How can I achieve that? Overall, in order to compare that, this node is equal to this node. Given a root of a binary tree, check whether it's a mirror of itself. So let me see. Let me think. So if that is the case, um, how can we get that? Okay, it is a symmetric tree. I think one way is we need there, like they explained, there was a top-down approach and there was a bottom-up approach. So in that case, like we need to keep passing both the trees or both the sides somehow, and then make sure that they are both equal and their children is also equal subsequently. If that is the case, then only we can achieve it. So let's see. I think we need to have two trees. Like only root is the single child, right? Other than that, the other ones will be like we need to check both the sides. So tree nodes, tree 1, tree node, tree 2. Let's see. Okay, here if root is equal to null, then we will return true. Otherwise, we will have to check. We'll have to check. Okay, something happened here. Let me check. The page is unresponsive. It's still loading. Okay, now it is loaded. Okay, what we discussed. Basically, when we see a tree, we need to know that, okay, its left subtree is also symmetric and its right subtree is also symmetric. And also we need to make sure that this one's left is equal to this tree's right. Or if it's the same node, they should be equal. So now you can see one, this is like, this could be any value. It doesn't matter if the tree is symmetric or not based on this value. But if this is 2, this should be 2. And if this is 3, like this tree's left child is 3, this tree's right child should be 3. This 3 is left child is 4. This 3 is right child should be 4. So here also we saw this tree, this is okay, this could be any value, but this one has a value 2 and this one must have a value 2, and this one has a right child 3. That means this one must have a left child 3, and this one has a right child 3. This one must have a left child 3, which doesn't satisfy. So this one was supposed to be here in order to make it symmetric. So now let's see, if root is null, then return true. Otherwise we will have to check. We can return is symmetric. We can pass root comma root as the true 2 variable, since we have 2 trees here, or we can pass root dot left and root dot right also. And we know 2 conditions. If this tree 1 is equal to null and tree 2 is equal to null, if both of those are null, then we can return it as true from that node. Like both of them are symmetric, both are null. And then if we know that okay, only one of them are null instead of both of them, tree 1 is equal to null, or tree 2 is equal to null, then return false. So this doesn't say that both of them are null. Like this says that one of them are null, but here we have already checked if both of them are null. If both of them are null, then we are returning true. If that doesn't satisfy, then only it will come here. This says that one of them are null, so then we will return false. If that also doesn't qualify, then we will check if the value is equal. If tree 1 dot node, or sorry, value, if tree 1 dot val is equal to tree 2 dot val, or if tree 1 dot val not is equal to tree 2 dot val, then we will return false. And then next thing is what we need to check is the current value is over current values. Now we need to check this one's left tree should be equal to this one's right tree, or symmetric to its right tree. So now we need to call, I'm just returning is symmetric of tree 1 dot left comma tree 2 dot right. And one more thing is the same or similar thing, tree 1 dot right comma tree 2 dot left. If both of those are similar, like tree 1's left tree is similar to tree 2's right tree, and tree 1's right tree is similar to tree 2's left tree, then that means the entire structure is symmetric. Let me see. Okay, 1 2 2 3 4 4 3, that is 1 2 2 2 3 4 4 3. So this is symmetric. So let's check for this example. That should give a false. Okay, that is false. Let's submit it and see. Okay, it's accepted, so it works. Let's move on to the next one quickly. Path sum. Given a root of a binary tree and an integer target sum, return true if the tree has a root to leaf path such that adding up all the values along the path equals target sum. So root to leaf, okay, 5 plus 4, 9 plus 11, 20 plus 2, 22. Target sum is 22. Only one path should be 22. The root to leaf path with target sum is shown. Okay, here in this one, 1 plus 2, 3, 1 plus 3, 4. So the total is not satisfied. There are two root to leaf paths in the tree. The sum is 3 and the sum is 4. So there is no root to leaf path with sum is equal to 5. Since the tree is empty, there's no root to leaf path. Okay, here, I mean, based on the explanation, we will see top down. In the top down, we will keep passing the value of its current node, and then we will know in the current value, and we will pass the target sum as well. If the target sum is equal to the current node value, then it will return true. Otherwise, it will return false. Okay, so we will see. Target sum is given, target, okay. We need another variable to keep the current sum also. Current sum also, not just the target sum, the current path value. So how do we do that? Current path value. So let's create a wrapper around this one. Okay. So here, int current path sum. Okay. So here, let's pass this one. Path sum root, comma. Maybe let's do it as root dot val. No, let's do it as 0 because we are starting from the root there. And then target sum, and we will return the same thing. And then here, if root is equal to null, return false. I am hoping root is null, target sum is 0, false. Okay, so if root is null, return false, or else we will call it as, and another thing can be if root dot left is equal to null and root dot right is equal to null, and current path sum plus, let's name it as node dot left is null, node dot right is null, current path sum plus node dot val plus target sum. Then we will return true, or else if root dot left not equal to null, then we will have to pass this one, pass this along. Left result. Node dot left. This is node, not root. We know from the left tree, left side of that path, node dot right side of the path, we know the solution. So now we need to see if either of them are true, then we will have to keep returning true. So if left path sum, let's mark it as something like this: boolean left path sum is equal to false. Right path sum is equal to false. If either of them are true, return left path sum, or right path sum. If either of them are true, then we will return true. Here in this case, if root is node dot left is null and node dot right is equal to null, and current path sum plus node dot val is equal to target sum, then we are returning true. Okay. Yeah, I think this one should work. If node is equal to null, then return false. If node dot left is equal to null, I think we can do this check at the top, I guess. We don't have to check that again because we are doing that left is equal to null, left not is equal to null, and left right not is equal to null only here. If in case root is not null, if root is null, we'll return false straight away. If root is not null, then we'll come here and then we are adding, just adding. If the left is not null, then only we are checking here. The right is not null, then only we are checking here. And current path sum, we just add that with the node value, and then if that is equal to target sum, then only we are returning true. Otherwise, we are pretty much returning false. Okay, here I'm returning false. But the expected answer is true. This is the example as we remember here, 5, 4, 11, 2. Let's run with this example and see in order to understand more. So in the interview also, we should do the same thing in order to troubleshoot. Let's not put a lot of pressure on ourselves. We will have the code side by side. We have written it, so we would know it. Okay, this did not print well. This was cool here. What happened? What changed? Okay, got it. So now we have come from the root. If root dot left is equal to null and root dot right is equal to null and current path sum, these both doesn't satisfy, so it will come to here. Left path sum is equal to 5, right path sum is equal to 5, node dot left not equal to null, then has path of node dot left comma 0 comma target sum. Okay, so this is the mistake we have. So as soon as I tried to troubleshoot it, we encountered the mistake. So we should not pass 0 here further down, so that would keep comparing it with 0 always. So this is the value. Node dot value is the base sum now, and then we need to keep comparing with that one. Let's run the code. Okay, still we don't have the answer yet. So anything obvious that I was just trying to check if there was anything obvious there. So I changed it to node dot val here. It should not be node dot val also. Again, the obvious thing is, let's make it as int current path sum is equal to node dot val plus current path sum is equal to current path sum plus node dot val. So, and then we need to pass the current path sum here. Not in current path sum, it's already instantiated. So this one. Okay. Still it's giving false. Okay, we haven't assigned the value here, just false, and false or false is equal to false. Yes. Initialize, define those things, but we didn't initialize. So many errors. Why am I making so many mistakes? I'm getting the pressure of live streaming maybe, but yeah, it's good that I'm identifying those during practice. Okay, let's copy this one now. Okay, we have this updated code now. Okay, we have 5 here. Current path sum is equal to 5. Okay, here another mistake is I already added the node.val to the current path sum, but still I'm trying to add it and compare it. So that should be one of the mistakes. So okay, true. If I submit it, yeah, this works. So let me explain how it works. So this is the thing I corrected here. Once we come to run, like our mind should work like a um, debugger troubleshooting this. I mean, we can use the actual debugger if it was real time, but that would tax our mind less. But here in the interview, all they are checking is how we are thinking about the code. So let's go ahead with that. So current path sum is 0 as we pass for the rule, and then current path sum will become 0 plus node.val, which is 5. So that is 5. And if node.left not left is equal to null, and so that doesn't satisfy, we won't come here. Left path sum false, this is false, and we keep checking for the left. So this left of this one, we are passing current path sum, which is 5, and then node.left. This for this node we have 5, and then we come here, we check the current path sum is 5 plus 4 is equal to 9, and then left is we still have the left node, so we come here. uh, 5 plus 4 9 we passed there, so 9 plus 11 20, it still has left node and right node, so we come here left node. So 20 plus 7 27. This doesn't have left node and right node, but still we come to with the path sum is not equal, so we don't return true. We will try to return true for this one. Like we are passing, we will return false for this one because this has left path sum already defaulted to false, right path sum is defaulted to false. No dot left, there's nothing in this one, so we won't get to this one. We won't get to this one. We just return left or right, which is false or false is false. So for this node, we return false. And then for this one, this part is done. No dot left. The right path sum we haven't calculated. So here until here we have 20, if we remember. So 20 plus the right path sum. So 20 plus we come here, we checked current path sum is 20 plus 2, 22, and then we check left, no dot left is equal to null, no dot left is equal to null, yes, no dot right is equal to null, no dot right is equal to null, yes, current path sum is equal to target sum 22, current path sum was target sum was 22, so yes, the 22, so that returns true for us, and then we keep returning left path sum or right path sum. It returns left path sum was false here for this node. Right path sum is true, left or right, so that will return true, and it will bubble up. For this one, left itself is true, so we don't have, it won't compute the right one, so it returns just true. For this one also, left itself was true, so it won't even go to compute the right one, so it just returns true. That's it. Simple. So submitted. Let's go to the next one. Count univalue trees. I'm not sure what are univalue trees. Let's see. Given the root of a binary tree, return the number of univalue subtrees. A univalue subtree means all nodes of the subtree have the same value. Univalue subtrees. A univalue subtree means all nodes of the subtree have the same value. Okay. So here the root is given, which is 5, and then the subtree of this one is 1. The root of return the number of univalued subtrees. A univalue subtree means all nodes of the subtree have the same value. Okay, all nodes of the subtree for this one is 5. All nodes of the subtree for this one is 5. All nodes of the subtree for this one is 5. All nodes of the subtree for this one is 5. For all nodes of subtree for this one is not 5. So that is not, this is not univalue, but these 4 are univalue. That's why I returned 4. In this case, there will be 6 univalue subtrees, each of those nodes basically. So what we can do is count univalue subtrees means, and what's the value? Like they haven't given the value, like if you need to check for 5 or even if you need to check for 4 or anything. Univalue subtrees, that's it. What if there were 2 different types of values? That's what I'm thinking. What if there were like 2 trees with value 6 and 2 trees with values 5? Is that possible? Let's try to have this one example. Okay, in this case, 1 tree, 2 3, 3 4 5 6 was the answer. Let's try to modify 6. What became 6? Now this became 6. So this subtree is not 6. So now it should be 4. Expected answer is no, no. Under this one is also there is a 6. So this is also not valid. This is not valid. So this is valid, this is valid, and this is valid. So this one also we can make 6. So this is 6, this is 6. So only valid for these two now. But we have 2 trees with 6 now already and 2 trees with 5. So let's make this as 6, not this. Make this one as 6. Okay, now these 3 are 6. So and these 2 are 5. So now what should be the expected output? 3. Missing return statement. Return just arbitrary number. Expected answer is 5 for this one. Okay, 5 for this one because, got it. Okay, 5. How 5 for this one? This is not a univalue subtree because there are different values here. There are different values here. But this one, under this subtree, all of them has the same value. So this is a univalue subtree. So this is a univalue subtree. This is a univalue subtree. 1, 2, 3, and this is a univalue subtree. So this has same value. This is a univalue subtree. Okay. So the value doesn't matter, but the current value and its all children's value, all that should be the same value. Then it's a univalue subtree. Got it. So let's see. So if a tree is a univalue subtree if its left child is a univalue subtree and if its right child is a univalue subtree and its value is equal to its left child and its right child both. That's when it makes it univalue subtree according to the definition here. So how will we compute the total number of univalue subtrees? Let's see. We can make it as the answer. We can have an answer as like this in an total univalue trees solution. Let's initialize it to 0 and then I think we can calculate here only. We don't need any wrapper for this one. So first thing is okay, if root is equal to null, then we will return it as 0. If it is not null, then what we will do? We will check int left univalue trees. Like we need to calculate the number of univalue trees in the left child. So that's when we will have this method called root dot left while passing root dot left, and then we need to calculate the right univalue subtrees. And then we will have this method call, and what we need to do, we need to see if when we will increment the number of the univalue trees. I mean, for the current tree or its parent tree to be univalue, current tree or its parent to be univalue, it is a must that all of its children are univalue trees. I mean, its left and right child both are univalue trees. If that's not the case, if its left is not a univalue tree and if its right is not a univalue tree, then the parent cannot be a univalue tree also. So if left univalue trees is equal to 0, or right is equal to 0, then what should we do? We should just return okay, that's not the case as well. What if the left is not 0 also? Even if there are some univalue subtrees on the left tree, even if that's the case, then also it's possible that the parent is not a univalue subtree. What I meant is, let's say in this example, even if this one is 5 and let's say this one is 1, if this is 5 and this is 1, even if that is the case, the left subchild is not a univalue subtree here, but right subtree is a univalue subtree. So the total number of univalue subtrees in this one is just 1. Total number of univalue subtrees under this one is 1, but this is not a univalue subtree, the current one. So it should return false, and this cannot be a univalue subtree since its left child is not a univalue subtree. Hi, Mr. 11. How can we know? Like first criteria is left also should be a univalue subtree and right also should be a univalue subtree, and then I'll be incrementing that with one more if the current value is equal to the left node and the right node, and then this whole thing would become a univalue subtree. Otherwise, I'll just know the count of the univalue subtrees on the left and count of the univalue subtrees on the right. So in order to do that, I need a way. So I need a wrapper here. So I'll create a wrapper method. So this one returns true or false. First thing is this one should return true or false, and then the total number of univalue subtrees also can be updated. So how can we update that as well? So every time we find a univalue subtree, we can just update the answer, I guess. Total univalue subtrees. But in order to figure out if it's a univalue subtree or not, we will follow this rule. So let's see. If root is equal to null, then return 0. And then here we can just return answer, which is total univalue subtrees. Otherwise, here left univalue subtrees, we cannot count that. If let's mark it as a node in this method. If node dot left is equal to null, and every leaf node is a univalue subtree, just in case. If equal to null, then return 1. And then if left is not equal to null, okay. Okay, if left is equal to null and right is equal to null, that means it's a leaf node. Then we will return it as true. And then we will have to increment as well. Before returning true, I'll increment this one. Plus total univalue trees. And then it goes to its parent. In its parent, it will check if instead of this one, is univalue subtrees root. Okay. And then here is univalue subtree, not trees. Let's mark it tree. No. Okay. If univalue subtree of dot left and is univalue subtree of node dot right, if both are univalue subtrees left and right, dot right, then we can increment it by one more, and that means the current tree is also a univalue subtree, and we can increment the total univalue subtrees as well. If not, and in this case I'm checking like if the left tree or the right tree has a null value, then how we will operate. If it's a null value, then we will just return it as true, but we won't increment the count of that. So if node is equal to null, we won't consider it as a univalue subtree, but we will mark it as return true. If we do that, we don't even have to check these two. if node is equal to node.left is equal to null, node.right is equal to null, then we don't have to check this one. We can just do plus plus univalue subtrees, because if node.left and node.right is taken care here, those are true, then we are incrementing here. This condition is not needed. Okay, so this should handle a lot of scenarios. Okay, if this is not the case, if one of them are not a univalue subtree, then we have to return false. My answer is 6 and expected is 5 in this case. Okay. Okay, what I'm doing here is univalue subtree of node.left and is univalue subtree of node.right. Then I'm marking that current one also as a univalue subtree, but which isn't the case. And I need to check if the value of the current node is equal to value of the left node and value of the right node also. So that is another condition. And okay, I'll write in the next line. So node.val is equal to node.left.val. Node.val is equal to node.right.value. Okay, so I needed that other null condition check now, because I need to okay, what I meant to say is, if it was null, like I thought this will handle the null conditions also. If left is null and right is null, I'm just incrementing it. But if left is null and right is null, I need to increment it. But if left is null, if left is not null and right is not null, then I need to check this value. So I need to have two different conditions there. So here, I don't need this one. I can just check if node dot left is equal to null and node dot right is equal to null, then I'm just returning true. Yeah. Here I'm checking if both of them are null, then I do this. If both of them are not null, if one of them are null, then how it is handled. There are so many scenarios here. If both of them are null, okay, and that means it's a leaf node. So let me comment. It's a leaf node. It's a universal subtree. and if it is, if either of them are not, either of children are not universal subtree, parent is not as well. Parent is not universal subtree as well. So what I can do is, let me break it down rather than confusing others and myself and the interviewer. So if either of them are, if both of them are universal subtree, then that means don't do this yet, go ahead. Otherwise return false. Okay. If either of them are not universal subtree, I'm going to return false. Now let's come within this one with another statements. If node.val, okay, one of them are, if node.left is equal to null, if one of them are null values, okay, one of them would be null here basically, because I have checked if both of them are null, I'm just going ahead and incrementing the value. I'm giving a go ahead. So one of them would be null. Like both of them are null, I'm going ahead. There can be one of them can be null or both of them non-null as well. So yeah, let's say if node.left is equal to null and node.value is equal to node. So both of them are not null. That's what we know here basically. So if left is null, then right is not null. So we can access this one. If node.left is equal to null, then node.right, I can check with the node.right.value. Right is not null. If that is the case, I will increment this one. Let me come to the formatting. Okay, I incremented this one. The other case is if node.right is equal to null and node.val is equal to node.left.val, then also do the same things. And then if not, if both of them, either of them are like not a universal subtree, okay. And then if both are not null, if left is also not null and right is also not null, then I need to check this one. If then I don't have to check that either of them are null or not. I can just return if either of them are, both of them are not null, then I can okay, I need to check the condition because I need to decide whether to increment it or not. If I need to check the condition of if the values are equal. If node.value is equal to node.right.value and if node.value is equal to node.left.value, then I'm incrementing this once. Got it. Okay, now I'm getting 5 as the answer. Visualize 2. In this case, 2 should be the answer. Okay, I'm giving it as 2 as the answer, but the answer should be 5. 1, 2, 3, 4. 4 should be the answer. 1, 2, 3, 4. So all these 4 subtrees should be the answer. So what's happening in my case? Five, 1, 5, 5, 5, 5. Okay, the same thing. Now I have the tree node, and if node is equal to null, I'm returning true. Node is not null. It's a leaf node. Okay, then it's here. I'm checking here. Node dot left and node dot right. Node dot left means again I'll go this one. Node dot left again. This one doesn't have anything. If node is equal to null, return true, and node is equal to, and node dot right, which is node is equal to null, I'll return true. So for this one, node dot left is equal to null and node dot right both are null. It comes here. Node is not null, and then it will make that total universal counts is equal to 1. This one, okay. And then I came to this node. So here node dot left, this condition doesn't satisfy, so this condition satisfied, and node dot right, it will come to the execution of this one. Here in this case, node dot left is null, node dot right is null, so total universal, this one I can increment it to 2. I incremented it to, okay, I incremented it to 2, and then it comes inside this one. Both are satisfied also, both returns true, and the node dot left is equal to null. For it came to we are in this method now. Left is not null. Node dot right is not null, so it won't come here. If node dot value is equal to node dot right dot value, no, it doesn't satisfy. It doesn't satisfy that either, so it won't do this part. So it will return as false. It will return as false. For this one, it checks. For this one, it checks. This one didn't work out. For this one also, this one itself is false, so this one just returns false. Okay, so I'm not even going to this one, so I'm just, my is universal subtree is not even checking for the right tree or going to the right tree. So what can we do now? We should iterate these two separately. I mean, we should not do it under AND condition, because we want it to iterate and check the total number of nodes in both of those, irrespective of the result from the left, because our intention is not to just know whether it's a universal subtree or not. Our intention is to count the total number of universal subtree. So now in this case, we counted the universal subtree only in the left, and we got to know that the current node cannot be a universal subtree, and we didn't bother checking on the right. So all we need to do is calculate this separately, and then here you decide. So let's go back. So what we want here, let's define a couple of variables here. Boolean is universal subtree left, because I'm updating the total universal values when we traverse. So that is important. Okay. Okay. So here right and make it right. So left and this one's right. Okay. So now these two will be executed irrespective of the result on the left side. The right one also will be executed. Now let's run it for the same example. 5 1 this one. Okay, yeah, now this should be 4. 5 1 triple 5. Okay, yeah, so the answer provided is 4 in this case. Now man, I have made few more. In this case 1 2 3 4, that should be 4. We know that both of them are not null. Left and right are not null. If both of them were null, we are incrementing it here. If the left is equal to null, then I'm just checking if the value is equal to right and incrementing. Else if right is equal to null, okay, I'm checking with the left. Else I'm checking, I'll have to compare for both of those, and I'm not checking the null, doing the null check here because both are not null. Then only it will come here. So okay, when I do else, I don't have to do this. Let's do else if only. Why it's not giving this one? Let's remove this. Okay, let's not spend more time. Let's get done with this fast. Okay. Now, okay, what do we have here? We have the problem. We are expected 4. We know why it should be 4. We know clearly 1, 2, 3, and this one 4 as a universal subtrees. Where are we making mistakes? Someone's right parameter is null, and we are not considering it. So where are we making that mistake? If node dot left is equal to null, where am I accessing node dot right dot val? Okay, node dot right dot val I'm accessing mostly in line number 54. Okay, what is the condition? I'm thinking through. If node dot right is equal to null, if both are null, node dot left dot node dot right, then I would just return here. If we have come till here, that means node dot left and node dot right both are not null. And if node dot left is null, then we would have come to this one. Else if no dot right is null, then we would have come to this statement. If we have come till here, neither left nor right is null. That's what my assumption is. But it is saying that the right is null. No dot right value is null. How can it be? What's the case I'm missing? What's the scenario I'm missing? Anybody? Need to look deep into this one. Node itself is null, then return true. Node dot left is equal to null and right is equal to null. That means it's a leaf node. Then return increment it and return true. If both left and right are universal subtrees, then only I'm coming here. If left is equal to null, then checking if node dot right dot val. Okay, got it. There is a possibility that one possibility node dot left is not. If node dot left is null, then we won't go here. If node dot right is null, we won't go here. If both are not null, then we will come here. That's what I meant. But if node dot left is not null, but if node dot value is this one, node dot value is not equal to this one, then we should have returned false in the beginning. So what we can do is not is equal to this one, then return false. Then here also node dot right not equal to null, then return false. Okay, and then okay, what I'm doing here is if node dot left is not null and node dot value of if node dot left is not null, then I have to check node dot left dot value. Okay, node dot left is not null and I'm checking node dot left dot value. If that is not equal to the node dot value, I can just plainly return false. I don't have to do anything. If node dot right is not null and if node dot right dot value is not equal to the current node value, I can just return false. If both of them doesn't satisfy, I mean one of them would be null or else this one would satisfy, then I'll increment the count and then I'm returning it as true. universal subtree of left or right itself is not true, then I'll return false overall. Total universal subtrees. Okay. And it's accepted. Man, I complicated it. Ah, these conditions, so many different scenarios, and we need to run it here. Yeah, this was clear mind. So all we needed was this null checks, and we did the null check here also. If both are null, that means it's a leaf node, and we will increment the total universal trees. And then if one of them are not null, then all we need to know is if the left subtree is, or the left child is not null, then we need to see that, okay, left subtree is universal subtree, and if the left node value is not equal to the current node value, then we will just return it as false. Current node value cannot be a universal subtree. And we are checking if the right node is universal subtree or not. If right node is also universal subtree, then we will check, and if not is equal to null, then we will have to check if the current value is equal to the right node value. If that is also true, if both are true, then I'm coming to else value, and I'm incrementing the total universal trees count, and then I'm returning true. And if either of them are non-universal subtrees, then we wouldn't even come to this if condition. We will return false right away. This is our code. I think it's pretty much up there. We struggled though, but pretty much optimal. Let's see how they have written. Okay, DFS of root and return count. They have initiated the count in the same way. Boolean of left, okay. Node is equal to null, then return true. Left is equal to DSFS node of left, same way as we did. And then if left and right both are universal subtrees, then only we are coming inside this. If left not equal to null and node.left.value not equal to node.value, then return false. Right not equal to null, then okay, I'm checking the right. Then if it's not equal, return false, and then incrementing the count and returning the true, else returning false. So exactly same logic. I'm kind of proud of myself, but I have an extra couple of lines of code that I realized I can remove. So here I'm checking here if the node dot, this will be like a certain this thing. If node dot left is not null, I'm checking if node dot left is not null, then I'm returning false. And if it's not equal, if let's say if node dot left is null, then it won't come to this one. Else if node dot right is not null, so if the node dot right is also null, then we will come to the else condition. If both of them are null, then we can just increment the total universal trees and return. Anyway, use universal tree subtree left, use universal subtree node dot left we will do if we don't check here, and then we will do node dot right. This is also null, this is also null, that would return true, true. So both of them will be true, true and true. It will come this side, and then it will increment. We can just save on this line of code. If it's a leaf node, then also that will be handled. So we are written. This is also accepted. Okay, nice. Let's move on to the next problem. So here, construct binary tree from in order and post order traversal. So these are like a bit tricky. I think I remember in one of the FANG interviews where I got selected for the first time, I think I had encountered something like a serialization, deserialization of a binary tree. So it was a long time ago, maybe over 10 years ago, or a decade ago. Just let's take a few minutes break, and then let's get back. It's 6:04 now. Let's start at 6:15, and let's wrap up these problems as soon as we get back. Okay, let's get back now. Okay, switched on the light there. Not sure if that is helping or not. Okay, anyway, the main focus is on the main screen, not on the side here where I am visible. Okay, given two integers, integer arrays, in order and post order, where in order is the in order traversal of binary tree and post order is the post order traversal of the same tree. Construct and return a binary tree. Okay, so we have this in order traversal 9, 3, 15, 27. Yeah, and then post order means left, right, and then correct. 9, 15, 7, 23. Yeah, that's right. So now we need to construct and return the binary tree. Based on this one, we need to construct and return the binary tree. How to do it? We need to return a tree node here. So, and then the tree's definition is given, val left, right, and then we have a couple of constructors to help us with that. So whenever the in order is given, we can derive a binary tree, but how, like, always it will be centered around, and we will be constructing a balanced binary tree, I guess. We just know that this is left and this is its parent. We might assume this also its parent, I guess. Let's see how we can think about it. So we have 9 as one of the node. What's the relationship between 9 and 3? How can we determine? So here in this example, 3 is given. So we know that 3 is the parent. So 3 is given. And then all these will be its children. All this will be its children. And then we know that 20 will be the left child if left child exists. Otherwise it would be on the right if left child doesn't exist. So how do we prove that it is the left child? You know that. Okay, here. Hey, hi, shot on iPhone. Okay. So how can we determine the order here? Or here we do not have any other relationship. Let's time box it for a couple of minutes because my thoughts are not flowing. So 3 is the first node. That's what we know here because that's the last element here. And then 20 is the next node, either in the left tree or the right tree. That is something we know. And then here in the left tree, on the left side, there is a 9. And we know that 9's parent is 3. Do we know that? Possible. 3's parent can be 15. Yeah, 9's parent should be 3. Yeah, let's look at the solution since we do not have a lot of clue here. In order is guaranteed to be in order. Okay, traversal of the tree, post order traversal of the tree. Next question is construct binary tree from pre-order and in-order traversal. In-order and post-order traversal. This one. Okay. Look at the solution. There are two general strategies to traverse a tree. Depth first search. The strategy we adopt the depth first priority as depth as the priority, so that would be the start of the root and reach all the way down to a certain leaf and then back to the root to each other branch. The DFS strategy can further be distinguished as pre-order, in-order, and post-order. Depending on the relative order among the root node, left relative order among the root node, left node, and the right node. Breadth first search is level order traversal. We can scan through the tree level by level, following the order of the height from top to bottom. The nodes on higher level would be visited before the ones on the lower levels. In the figure, in the following figure, the nodes are enumerated. In order you to visit them, please follow 1, 2, 3, 4, 5 to compare the different strategies. Okay. Here in this case, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. This is like pre-order traversal, right? Yeah. Root dot value plus pre-order of root dot left, pre-order of root dot right. Okay, root dot value. This is GFS pre-order.
The volume is currently set to 90%.
Okay. DFS in order, DFS pre-order. DFS pre-order means root value, root dot left. Okay. If root, else return just empty list. In order traversal. Okay. Yeah. DFS post order. This one. BFS means iterations with the queue. One deals with in order and post order traversals. How to construct the tree from true traversals in order and post order. Problems like this one are often at Facebook interviews and could be solved in O of n time. Start from not in order traversal. Usually it's a pre-order or post-order one, and use the traversal picture above to define the strategy to pick the nodes. For example, for pre-order traversal, the first value is a root. Okay. Then its left child and its right child, etc. For post-order traversal, the last value is the root, then its right child, and then its left child, etc. Okay. The value picked from pre-order or post-order traversal splits the in-order traversal into the value picked from pre-order or post-order traversal split the in-order traversal into left and right subtree. Great. So we know that 3 is the first one. So everything on the left to 3 is the left subtree. Everything on the right. So we know that this is the right subtree. 15, 20, 7. Let's assume this way. Okay, 7, since when we have only single node, we don't have to do anything. There's 9, it's sorted here, like that's how it will be. And 3's child will be this one. And here on the right side, it's 15, 20, and 7. And here, 20 is given first. So that means we can just to write 20, I guess. I think so. The second step will be, let's copy from this one. This can be step 1 and this can be step 2. Here we know that 20 is printed first in the post order. So I can put 20 here, and then this one can be 15 and 7 as the left and right basic. So that means 20 is picked, 15 on its left, so 15 should come to the left subtree and 7 should come to the right subtree. So 15 and 7 like this, and from this one we know 15 is left and 7 is right. So okay, so it looks like this from my deduction. Okay, let's 3 and 7, 3 9 20 15 7 9 20, not 19 20, 3 9 20. Yeah, so this looks right. So I understood the logic how they are getting into it. The value picked from the pre-order or post-order traversal splits the in-order traversal into left and right subtrees. The only information one needs from in-order is if the current subtree is empty, return none. Otherwise, if it's not empty, then continues to construct the subtree. Okay. So build a hash map, value its index, value to its index for in-order traversal. Return a helper function which takes as the argument the left and right boundaries for the current subtree in the in-order traversal. Okay, these boundaries are used only to check if the subtree is empty or not. Here is how it works. Left is equal to 0, right is equal to n minus 1. The subtree is empty. Return none. Pick the last element in the post order traversal as a root. Okay. Root value has an index in the in order traversal. Element in dot left to in dot index minus 1 belong to the left subtree, and elements from index plus 1 to in dot right belongs to the right subtree. Following the post order logic, proceed recursively first to construct the right subtree, index plus 1 dot in dot right, and then to construct the left subtree, return the root. Okay, this makes sense. We have a hash map, left subtree, Okay. This seems to be good, but let me see if I understood it completely. So here, what's the significance of this particular thing? Index, post index. So post index is the index in the post order, and I keep navigating that. Okay. Got it. So over here, all I should have is int current post, or just post order index in, okay, and then I can have index map, okay, and I'll create a constructor for the same thing. And I'll instantiate the post order index to post order dot length -1, and then index map is equal to new hash map. So map will be between integer and integer. So now let's do if in order dot length is equal to 0, return null. And the next thing is int element in order. I'm just traversing through each of those, and then I need to just add it to the map. Index map I'm adding the element and its index. So I need a index based loop. So here in order of I, and then I'll add its index here. After that, I need to start building a tree. Build pre-recursive, and then I'll pass in order, post order, and then 0, comma, post order index. here. Okay, let's keep it simple. Let's try to initialize it. Not in this one, but okay. And I don't need these things now here, and it from mark it up from index and to index. Now again, if from index is less than to index or greater than to index, return null. Otherwise, we know that current value is equal to post order index, and then node is equal to new node of current value. So we created the current node. Finally, we need to return the current node only. But how do we generate the left node and right node? So node.left is equal to, again we will call the same thing recursively, from index to the okay. So in order index is equal to the value that is provided. Index map dot get current value. So get that current value. So that will be in order index. So how we build the left tree from in order index to the from index, and how do we build the right tree? From index that would be in order index to index, and this one will be from index to in order index. Probably -1. Yeah. Yeah, because we already used up the current, whatever the element is in order index, that current value is already used up. So from index to in order index -1, and in order index +1 to index. Okay. First thing is this one. We just removed it and made it as a class level instance operators. Should be new node, not just new node. Okay, I did not build any current node. So this okay, we don't have the post order index as of now. So how can I define it? That was stupid of me. Okay, I missed this one, decrementing this post order index value. Get root value. Okay, and this one node dot left, and this should be node dot right. Okay, it looks similar. In which case my okay, why in which cases it's going to negative? It looks like I have kind of similar code or similar implementation to what it is in there. Initialize the hash map, integer, okay. Here, post order, pre-order. Okay, I've got that. And post order index is equal to post order dot length minus 1. I got that. I've created. What is that? Another index. Index is equal to 0. Build a hash map value. The index. Post order length minus 1. If post order length is this order is interchanged there. That doesn't matter. Oh, that did matter. How is that order is so important? We need to build the right subtree first and then the left subtree. Following the post order logic, proceed recursively first to construct the right subtree, post order logic, and then to construct the left subtree. Root value has index in the in order traversal elements, okay, the left subtree, and the elements from index plus 1 in the right subtree belong to the right subtree. Okay, let's take a quick break of 2 minutes. Okay, let's get back now. So yeah, this is the one. So yeah, we just recreated or built a tree when the pre-order and post-order traversals were given. So that's the problem, right? I think this is the problem. Yeah. So pre-order and post-orders were traversals were given. We needed to reconstruct the tree. So sorry, in order and post-order were given. We needed to reconstruct the tree. So here uh, we had this one. So I'll just revise how we did that. So we have the in order traversal. So all we know is from this logic. So we know that in the post order, the last element would be the node. So that we know. So we know that last element is the node, and we get the last element's index in the in order. In the in order, we know all the elements to the left of this one would be the left tree, and all the elements to the right of this one would be the right tree. So now we know the 9 would come to the left tree, and then this 15, 27, these will come to the right tree. But we don't know the order in this one. So here after 3, we decremented it and came to 20. So now 20 we know is the root of that tree, wherever it belongs. So we got to know that 20 is the root of the tree, and 15 and 7 are the children in those tree. And we got to know from here what is the index of 20. So index of 20 is this one. So here, based on this one, 20 is the index. Based on this one, like we are trying to find the, so we've already built the left tree 9, which is a single node there. So in order to build the right tree, we have these 3 elements 15, 20, and 7. So we got to know 20, index of 20 is this one. So everything to the left of this one is the left subtree, and everything to the right of this one is the right subtree. So everything to the left of this one is 15 is here. Everything to the right of this one is 7. We built a reconstructed the tree. And in the code, if we have to look into this, so I need a map in order to get the index of the element in the in order traversal. So I created a map for the in order of I. This is the index. So this is the value and this is the index. And then I created a recursive function, build tree recursive, and I'm passing the index 0 and then the post order index. Post order index is the post order length dot one in order to avoid confusion, or it can be like in order. So like the total, in order to avoid confusion, total number of elements basically, the last index of that particular this thing. So here now I'm checking if the from index is greater than to index, then return null, or else the current value is equal to post order index. Post order index is something that we defined here. Post order index is post order length minus 1. As I said here, we know that the last element in the post order traversal, that would give us the root node. So because we know the post order index, post order traversal, right? I have explained it before. Post order means left, right, and then current node. So here in this case 9, and then right means right subtree, not just the right node. In this one again left, which is 15, 9, 15, and then right, which is 7, 9, 15, 7, and then the current node 20, 9, 15, 7, 20, and then left and right are done. So now 3, 9, 15, 7, 23. So the node is printed at the last. We know that the node comes at last. That's why we have defined the problem here. We in the whatever the post order length, that post order index that we have, that would be the current node. So the current value is this dot post order of this one. Like in the post order index, whatever we have, that's the value, and created a node with that one, new tree node, and then we decremented the post order index by 1. And after that, in the in order index, we are finding the index of that particular value, current value, whatever is there. We are trying to determine the index of that one. So what's the index of this 3? That means current value is 3. What is the index of this one? This is 1. So now we are trying to create a tree of the elements on the left side of this one and assign it to the left of that current tree that we create, tree node that we created. And then whatever the elements on the right of this one are there, we will try to create a tree out of that one and assign it as a right child. And that's what we are doing here. We have the in order index. Node.write is equal to build tree recursive in order plus 1 and then 2 index. In order plus 1, in order index plus 1 to 2 index. In order index plus 1, which is in order index is 1 from this one to this one to the final. And then for the left subtree, only this one. Okay. In order index minus 1. Okay. And then it is not greater, it will come here and then we will print the current value. And then once it gets greater, left and right will be null to 9. But the current one will be 9 on the left subtree. But another key thing to notice here is the order of this one, node.right and node.left. So why this order is important? If we try to create the left subtree, it fails because the from index and in order index, these things are the same values, like even if we interchange the order. But the post order index, which is there, which we are defining it in the at the class level or the index or the instance variable or as an instance variable. So that would be different. Like if we try to define left first, so it will try to think of that left as first thing. Here the given thing is post order traversal and then the in order traversal. So this post order index follows the post order procedure. What happens in post order? In post order, first thing is left, right, current, left, right, current, like that. So if we know that it's the current value, this would be the right tree or the right value. And then this would be the, right tree following this one. So since we know that, okay, this is the current value and this is the right one, which is followed, we need to construct the right tree first and then we go to the left one. So we are basically reversing that order here. So it should be left, right, and current in the post order traversal. What we are doing is current, right, and left. So that way we are building it recursively. Since we are putting it to the stack, recursive stack, we are reversing the order also. So if we submit it, it is accepted. Let's move on to the next one. So in this one, pre-order and in-order are given. Pre-order and in-order. We can follow something similar, somewhat similar approach, I guess. So let's see. In this one, pre-order and in-order are given. So in the pre-order, like we know that the first element is the root node. So in the pre-order, current, left, and then right subtree, and then current, left, and then right subtree. This way it is handled. So in the in order, it's the same thing, left, current, and right, left, current, and right. So let's get to this one. We will follow something somewhat similar to what we followed in the last one. Int pre-order index is equal to 0. We start last one for the post order, we started at the end. Here we are starting in the beginning. So that's one thing. And also one, we have to create a map of in order index. In order index. And then also let's keep these things at the top level. And let's instantiate whatever we can in the constructor here. Only we can instantiate the map here. In order index map. We instantiate the map, and then here in the build tree, let's instantiate this pre-order and in order. And then let's instantiate this in order structure as well. So next thing is we need to instantiate this pre-order index that is already instantiated to 0, but we can move that to here. Okay, so once that is done, we need to populate that in order index map. In order to populate that one, yeah, let's populate that first. We need the index based looping in order to populate it. Okay, then we have this in order index map. In order of I, and then I. Okay, now this one is populated. After that, hi Akhil. After that, next thing is we populated this hash map. Next thing is we will go to we will call the recursive method for build tree. So build tree recursive. What all parameters we need? We don't need the pre-order and in order, but we need the starting index. Like we are dealing with the whole tree now. For example, this one. Let's keep the index of this one. Now we need to construct the recursive function. So I'll just trying to copy the signature here. It can be a okay. Akhil, thank you for letting me know. Is this better now? Is the voice is better now? Okay, thank you. I think all the settings are intact, but yeah, let me continue. Let me know if you still have trouble hearing me. So thank you, Akhil. Okay. So I got a feedback that voice is low, so I tried to correct it. So now the next thing is okay. I need to build this one. So this is build tree recursive. I just tried to copy the signature. Let's remove this one, and then we need to. So what we did in the last one, we will try to do the same thing in reverse. If so here this is not int pre-order and post order, int from index and int to index. So here if from index is less than or it's greater than to index, then we will just return null. Next thing is if it is not greater, then it is like int current value. We can get the current value is equal to pre-order index, pre-order traversal of pre-order index. Okay, and once we get the current value, we can create a current node. Node is equal to how we can get it? We can get this from this index map that we have created. We need to get the value index for this value. So that is done. So the next thing that we and then we need to increment this pre-order index as well. And now next thing is, so in the pre-order, what's the order that we go with? usually in the pre-order, current node and then the left index and then the right index, or current node and left tree and then the right tree. So here we can construct the right tree and left tree and then get the current node. Current node, left tree, right tree. Okay, since we are coming from the right direction here, like there we were coming in the reverse direction in the pre-order traversal. Here we are coming from the forward direction. So current tree, left tree, right tree. We will follow the same ordering. So current node dot left is equal to we will try to build this recursively. And okay, this is the this one is current node is equal to new tree node of, okay, I didn't notice this one. This one should be the in order index. Let's keep it as in order index or current index. Yeah, current index is equal to, we are getting it from here. And how do we build from index for the left node? From index remains the same, and then we will build until current index -1. And for the right subtree, we will build from current index +1 to 2 index. And once it is done, we need to return the current node. Okay, so okay, so this one is private. I haven't mentioned the type here. Okay, in order index map. Okay, this is also, how did I get this into here? In order index map of I, I. Array required but map found. Okay, this is not in order index map. It should be in order. Yeah, while building the map. Okay, now it is finished. Yeah, let's submit this. And it's accepted. So this is the code. Why did I made it as index ++ left and right here, whereas in the pre-order traversal, sorry, when the post-order traversal was given, in order index and then right and left. So in this one, we were kind of traversing from the reverse order of this one, post-order output that is given. We were traversing from behind, from the last index to the first one. In this case, and then what is post-order? Post-order traversal means current, left and right. So when it's current, left and right, but we were traversing from reverse direction. So what we were making current, sorry, let me reiterate. In the post-order traversal, it is left, right and current. So, and we were traversing from the reverse direction. So we needed to reverse it. Left, right and current, I made it as current, right and left. So that's what we constructed here. This is current, this is right, and this is left. And when it came to this, when the pre-order was given, pre-order traversal is given, we are traversing from the forward direction. So we don't have to reverse it. And in the forward direction, pre-order is current, left, right. And we did the same thing. Current, left, right. And this one I think we can avoid by doing ++ here. Yeah, that would save a line at least, and makes it more readable. So same thing applies here. Post order index. Let's mark it as minus here. Okay, got it. So this one, let's move on to next one now. Hey, Kil, are you still there? Let me know. Welcome to the stream, and let me know if you have any questions. Okay. Populating the next right pointers in each node. So in this case, I think we had seen this one when we were solving for graph. So here, every node is having current value, and then left and then right subtree. With that, it has a next pointer as well. So when it has next pointer, the next should point to the right subtree if it has some value. So we can explain it again. Let's yeah. Oh, I think I could have used this one, reset to default code configuration. Okay, yeah, now there's nothing in this one. So populate each next pointer to its next right node. In the diagram, it's kind of clear. In the same level, if there is a next node, then we have to populate that value that node value in this pointer. So yeah. So for 1 it is null, for 2 it is 3, for 3 it's null, for 4 it's 5, 5 it's 6, and 6 it's 7, and 7 it's null. Okay, this is kind of easy if we have understood breadth first search and we know about the tree structure. So how do we do the breadth first search or the level order traversal? Level order traversal usually follows, like we will follow this level, and then we will come to this level, and then we will come to this level. While following that level order traversal, what I was doing in the same level, we will see, like, yeah, when following this level, there's nothing after processing this particular element, so we will point it to null, and then we would have populated the next level as these two elements. So when we come to address this level, so if I'll see, I took this from queue, and then if there are still more elements in the queue, then I'll just assign the peak value in the queue to as the next reference for this particular node. So 2 should point to 3, and then after 3 there's nothing in the queue in the same level, so I'll point it as null. So yeah, that was kind of straightforward. Let me explain by looking at it here as well. So I'll take two queues, one to hold the value in the current level and another one to hold the value in the next level. So let's do that, and I'll populate the route to the current level. I populated that. Next thing what we need to do is we need to traverse through that. So in order to traverse, I'll follow a while loop. Once I'm following this one, what should I do? First thing is node current value is equal to current level. I'll just pull from that particular queue. I got the current value now. So now I need to figure out the next value for that particular node, or then this is the node. So node has that next value or reference for the next value. So how I would assign it? So current dot next will become current dot next is equal to I'll check the current level queue. If there is a next value, it will be actually the next value in that queue. So I'll just peek from that, and if there is any value, I'll just assign the reference for that one, and then I'll see if it has left, like it has to go from left and right in the tree also in the same order. I'm just trying to preserve the order. In this level I have come, so 2 and 3 are in the queue. So 2 I'll assign 3 as the next value, and then to the next level I'm adding left subtree, which is 4, and then right subtree, which is 5. And then I came to 3. To the 3 there's nothing in the current level, so I'll assign it as null, and then I'll assign the left subtree, which is 6, and then I'll go to the right subtree, which is 7. So that's what I'm doing here. So if current dot left not equal to null, then I'm just adding it to the queue. Current level dot offer current dot left, and I'll do the same thing for the right. So here yeah, I did that. And then if current level dot, if that gets empty, like once we process the current level, then we should move on to assigning next level as the current level, and I'll instantiate the next level into a new value. So that will be done by this statement again. And then what I need to return the root node only. So that should do the trick, but I always get confused in this one. Okay, it's finished. It looks pretty different though. 1 2 3 4 5 6 7. Okay, I have offered current to the next current here. Current dot left not equal to null, current level dot offer current dot. Okay, this one should be added to the next level, not to the current level, because its left child and right child are in next level. So now you can see it's similar, and we are okay. Another thing, if root is equal to null, just return null. Yeah, it's accepted, and we are done with this. Let's move on to the next problem quickly. Populating next right pointers in each node. 2. It's the similar problem, I guess. There might be slight variation. Populating each next pointer to the right node. If there is no next right node, the next pointer should be set to null. Initially, all next pointers are set to null. Okay, what is different here? You may only use constant extra space. The recursive approach is fine. You may assume implicit stack space does not count as extra space for this problem. Okay, so we need to do it using recursive approach because we cannot use additional extra space. In this one, you can see the extra space that we were using in the previous approach. We were using the O of, not O of n, O of log n, I guess. It is because we were storing only 2 levels worth of information. So in this case, that space should be a constant space. So how can we go about it? So if we can use only a constant space there, that means they are telling we can go with the recursive approach. In order to go with the recursive approach, okay, we have the current node, we have its left node, then its right node. So current node's right node is the next for this one. So its parent's immediate right node is its next node. No, for this one 7 is the right node. So it's not even parent's right node. So how to go about this one? This could be, I just want to see if it's a, what's the difficulty level of this problem? What was the difficulty level of this problem? The previous one we solved was a LeetCode medium. And this one that we are seeing, this is also a LeetCode medium. Okay. Recursive approach is fine. Let's give it some more thought or some more time. Given the above perfect binary tree, your function should populate each next pointer to point to its next right point, just like in figure B. The serial as output is in the level order as connected by next pointer, with hash signifying the end of the each level. Okay. Recursive approach is the only way, I guess, like we can go about in order to maintain a constant space, because they are telling you may assume implicit stack space does not count as extra space for this one. So there will have we will have stored values for these ones, which should go next. So there's a left subtree and right both. Somehow I'm seeing if it's 7, then 6 is kind of easily traceable because its parents left. I mean, for 6 I can relate to 7, but 5, in order to relate to 6, that's a bit tricky. It's not directly related to its parent, but parents, and then longer ancestral chain I need to follow. So in order to do that, I need to store 6 somewhere and then address these things. Let's look at the approach here. Okay, here space complexity is of n in this approach. This is a perfect binary tree, which means the last level contains n by 2 nodes. Okay, the space complexity for the breadth first traversal is the maximum space occupied by the space occupied by the queue. Okay, that's O of n. So this is same as what we addressed there. Using previously established next pointers. Okay, we have to process all the nodes of the tree, so we can't reduce the time complexity any further. However, we can try and reduce the space complexity. The reason we need a queue here is because we don't have any idea about the structure of the tree and the kind of branches it has, and we need to access all the nodes on a common level together and establish connections between them. Once we are done establishing the next pointers between the nodes, don't they kind of represent a linked list? After the next connections are established, all the nodes on a particular level actually form a linked list via this next pointers. Based on this idea, we have the following intuition for our space efficient algorithm. Nice. I think I got the gist of it. So for 1, there's no next pointer. For 2, okay, its parents, this one, that is the next pointer. So for 5, I don't have the its parents right again, but since there is no right, I'll go to its parents next pointer and its left. Parents next pointer and its left. Yeah, parents next is 3 and its left subtree. Or if left doesn't exist, then the right subtree. Yeah, that could work. That could work. But yeah, how do we even store which one we are traversing through? Okay. For 1, I have the left as, okay, 1 null, and then I have 2. 2, the next pointer is 3. Okay. And then I should just hold the value of this one. I come back here, 4. The next subtree is, okay. Yeah, we start at the root node. Since there are no more nodes to process on the first level or level 0, we can establish the next pointers on the next level, that is level 1. An important thing to remember in this algorithm is that we establish the next pointers for a level n while we are still on level n-1. And once we are done establishing these new connections, we move on to n and do the same thing for n+1. Got it? As we just said, when we go over the nodes of a particular level, their next pointers are already established. This is what helps get rid of the queue data structures from the previous approach and helps save space. To start on a particular level, we just need the leftmost node. Okay, we just have to save this only. Yeah, that intuition was right. Based on these ideas, our algorithm will have the following pseudocode. Leftmost is root, while leftmost not equal to null. Keep going. Current is equal to leftmost. Okay. Previous is equal to null. While current not equal to null, process the left child, process the right child. Set the leftmost for the next level. Set the leftmost for the next level. How? Leftmost should be leftmost left child or right child. Okay. Got it. Before we proceed with the steps in our algorithm, to understand some of the variables we have used in the pseudocode since. Okay. While this dot leftmost not equal to null. Okay. Okay. It is, the approach is clear, but the code isn't. Process child. Okay. Let's see this one. If child node not equal to null, okay, let me make more sense of it. Root is equal to null, then we return root. Okay. Leftmost is equal to root. Current is equal to leftmost. Okay, that is clear. To find the last level, the nodes on the last level won't have any children. Okay, so that leftmost will become null. Previous tracks the latest node on the next level, while current tracks the latest node on the current level. This dot previous is equal to null. Okay, latest node on the next level. Current is equal to this dot leftmost. Got it. And this dot leftmost will be null because this is tracking the next level. While current is not equal to null, current not equal to null, current is equal to current dot next. This dot process child current dot left, this dot process child current dot right. So how to process it? While processing, if child node not equal to null, child node is null, then done. If the previous pointer is already set, that is, if we already found at least one node on the next level, set up its next pointer. If this dot previous not equal to null, then this dot previous dot next is equal to child node. And then return this dot previous is equal to, and this dot previous is equal to child node. It will become previous will be next. If this dot previous is not equal to null, if this dot previous is equal to null, that means in the next level there is nothing. So this dot leftmost will become the child node. And then this dot previous will be the child node as well. Okay, it's kind of clear now, but I hope it's intuitive. This recursion is kind of too much time consuming or too much thought consuming. Let's see. So in this case, okay, let's try to code it up and see what I'll encounter. So in this one, what we were saying, if root equal to null, then we will just return. Let me shut this door. There's some noise. Okay, let's get back here. So if root is null, then we are returning it as null. And next thing is leftmost. Here we will, let's define this one. Private int leftmost. Leftmost signifies the leftmost in the next level. So private int previous will be the previous in the next level. And then private int current. This signifies the current value that we are dealing with in the current level. So here leftmost is equal to 2, and then current is equal to leftmost. Then to check while current not equal to null, I'm iterating through this. Current will be current dot next, and then here what I need to see, if current dot left not equal to null, then process child of current dot left. Okay, and then current dot right not equal to null, process child of current dot right. Also process child here. Okay, so not renode, just a node. Okay, process child. If here, what we will do here, previous not equal to null, then previous dot next is equal to the node that is passed, and then previous will become equivalent to node. If previous is null, that means leftmost is equal to the current node, and then previous will become that leftmost or that node itself. And here I need to assign null to the leftmost node, and previous will be assigned by as it is, I guess, right? So I don't need to do anything, I guess, if I remember correct. Root is equal to null. Okay, root is equal to null, return. Okay, null. Leftmost is equal to root. Current will become leftmost, while this dot leftmost not equal to null. While this dot leftmost not equal to null. That is something which I did not understand. Okay, while this dot left, that's the outer loop, where that means we are at the bottom most level. Well, this dot leftmost, that means there are no levels further. While there aren't any more levels to process, what we will do, okay, this dot previous is equal to null. Previous is equal to null. And then current would be equivalent to leftmost. And then we will mark the leftmost as null, because here we are starting a particular level here. So we assigned root as the leftmost. So now the previous is null and current is leftmost, and the leftmost for the next level is null as of now. And then when we come here, while current is not equal to null, process the left child and then process the right child. I don't think we need to check this one, null check, because process left child and right child means that would assign null values only to that one, I guess. Yeah. Okay. Process the left child, process the right child. This is not current is equal to current dot next. Okay, this is node leftmost, this is node previous, and this one is node current. Process this one, returns void, and and this one returns true. We don't need this parent outside anyway. Okay, here we need to check if node is not null. Yeah. Okay, this was pretty difficult to map to our brain, this recursive approach. So it's this one, populating next right pointers to each node. So starting, we took the logic that we have used here. We are checking if the node is null, then it's straightforward. We are just returning it as null. And then we are initiating the leftmost. Leftmost means the leftmost in the next level. So that's what is leftmost, and that we have been holding in the as a class, as an instance variable in the class. And then once that is done, so now we are at -1 level. We haven't even started at root. So we are at this level now. We need to process this level next when we are at this level. So I have assigned root as the leftmost for the next level that we are going to process. And then current will become the leftmost. Current will be the leftmost. Now we are iterating through this one, while leftmost is not equal to null. While leftmost is not equal to null, we are processing it. So previous is equal to null now. Previous is null. So previous is null means the previous element in this next level. Okay, the previous element in the next level is null, and then the current is equal to leftmost. So the current value is the leftmost. So that means I'm assigning the leftmost value to the current. So it's like initiating the next level. So this is like a level order loop, and this is just looping through that particular level and marking the next pointer to the next value in that particular level. So this one, in this level, I'm just assigning the values. Previous is null, current will become leftmost, and leftmost will become null as well. So once that is done, okay, let's do it this way. Yeah, initiated the current value to leftmost and assigned the previous and leftmost to null. After that is done, while current is not equal to null, I'm doing current is equal to current dot next. And I'm processing the child of the current dot left and current dot right. This is, I'm processing the next level, not the current level. So that's why I'm passing current dot left and current dot right. In the next level, what I'm doing. So if in case in the next level, how I'm processing. If node is null, then I'm just returning, doing nothing. If node is not null, and then if previous is not equal to null. If the previous is not equal to null, here in the first case, previous is null. So what I'll do is I'll come here, leftmost is equal to node. I'll assign leftmost is equal to node and previous is equal to node as well. So leftmost will become node. So in this case, if we consider leftmost will become node. When I came to 1, leftmost will be, and then I asked to process the left child, and then I asked to process the right child. And then the leftmost I had assigned to null, previous I had assigned to null. So the leftmost will become 2, and the previous also will become 2. And then I came back to the same thing, and then I asked to process the right child. In this case, the leftmost is already 2, and then the previous is already set to 2. So since the previous is not null, previous dot next is equal to node. So previous was set as 2, previous dot next is equal to current node, which is 3. And then now the current dot next is equal to null. Current dot next is null. Current dot next was null. I mean, one dot next is null. So I won't go there. So this loop is exited, and then I'll come back here. And leftmost not equal to null. So leftmost is not equal to null now. Leftmost was assigned as 4, 5. Leftmost was assigned as 2. So now I'll come back here. Current would be equal to leftmost. Current is leftmost, previous is null, and leftmost is null. While current is not equal to null, process current dot left, current dot right. Current is equal to current dot next. Okay, current not equal to next. Current not equal to null. Current not equal to null. Current dot left, process current dot right. Here this is assigned as leftmost, and this is assigned as previous as well, since leftmost was null, because I instantiated leftmost and previous to null in this case. And then current will become equal to current dot next. Current dot next, again left is null, so I would exit, and then I'll just process the 7. While processing it, previous dot next, I'll mark it as 7.